I'm going to kind of, modulo Wayne's you justified false belief issue from earlier, I'm going to kind of try to cover two half topics worth of material which are interrelated in certain ways. What I want to do in the first half of the presentation is suggest a certain way of thinking about a disagreement one can have in physics between two different ways of reading a scientific theory or the point of a scientific theory, and try to use that to provide a certain framework to think about the nature of some of the disagreements that you see in philosophy of statistical mechanics, and perhaps in some way try to help understand how it is that various people can talk past each other in discussions of these kinds. And what I'm going to do in the second half is apply that in a rather detailed case study of a certain aspect of how that plays out, although the case study is mostly interested for its own sake rather than because of the connection. So, what do I mean by an inferential versus a dynamical conception of a theory? I should say incidentally, I'm not going to particularly try to defend the claim that either of these is the right way to read any given scientific theory. You can probably guess, or you will be able to guess if you can't already, where my sympathies lie, but I more want to try to lay out a kind of framework for thinking rather than advocate taking a particular position in that framework. And the distinction I want to suggest goes something like this. For a given bit of physics, I'm not talking about something you do for physics or science as a whole, but for a given bit of physics, an inferential conception on that theory says that the job of that bit of physics is to help us, the agent, the knower, the observer, to make inferences about the past or present or future goings on in the world on the basis of our partial information about something. On the dynamical conception of a given bit of physics, then the point of that particular bit of physics is to understand certain dynamical laws that govern systems, independent of whether there are any agents around, independent of our knowledge of those systems, simply as one of the various facts about the world that science is trying to study. These are kind of intended as, I guess you might say, ideal types. It's not necessarily the case that any given position, or indeed any plausible position, sits entirely on one end or the other of the spectrum, but I think the distinction is somewhat helpful. So what I'm going to do now is show how that runs in statistical physics in particular. I'm then going to kind of compare that to a similar kind of question you could ask in quantum physics, and then I'm going to show a connection between those two by looking at how it plays out in the quantum mechanical version of statistical mechanics. So just to put some of that up, I'll be reiterating this quite a lot, so just to be clear on what it is. There's the inferential conception. I know I have partial information about the system. I want to make inferences to the best accuracy I can, given my knowledge of the state of its history. Now, conception, there are systems, they evolve, various properties of theirs satisfy certain dynamical equations. I want to know what those dynamical equations are. I want to know, insofar as I can, why they hold. The question of how agents' knowledge figures into this is neither here nor there.
David?
Yeah.
I mean, probably this is the answer to my question is, that's just my point, but these aren't on the face of it incompatible conceptions at all, right? I mean, knowing, having the kind of knowledge described in the second will certainly help us with the first, say, or something like that.
Oh yeah,
right.
Yeah. I mean, I suppose distinguish, there might be, there might well be situations where, I use the term bit of physics as a deliberately vague term rather than say theory or defined subdiscipline. It might well be, for instance, that what one sees as a certain bit of a given theory needs to be thought of as an inferential task carried out against the background dynamical understanding one has of another bit of the theory. So all sorts of things like that are possible. Okay, so let me show how I think this plays out in StatMech. So here's a kind of quick sketch as to what the inferential conception of StatMech is. So we don't know a system's microstate. Even if we did know a system's microstate, we can't calculate its precise dynamics. Statistical mechanics is in the business of helping us get information about what systems are going to do, about what I can predict about measurements on a system, on the basis of that highly partial understanding of the system and the system's dynamics. So here's a kind of Classic quote from Tolman's book, giving this kind of conception of the subject. Science of statistical mechanics has the special function of providing reasonable methods for treating the behavior of mechanical systems under circumstances such that our knowledge of the condition of the system is less than the maximum knowledge which would be theoretically possible. On the dynamical conception of statistical mechanics, it's more like this. Statistical mechanics is about studying the dynamics obeyed by the collective degrees of freedom of big systems. So I have systems with many degrees of freedom. There are objective dynamical facts about the equations that seem to govern the large-scale collective degrees of freedom of those systems. I want to know what those equations are. Here's a quote supporting that position. Systems such as a gas composed of many molecules is actually found to exhibit perfectly definite regularities in its behavior, which we feel must be ultimately traceable to the laws of mechanics, even though the detailed application of those laws defies our powers. But the treatment of such regularities in the behavior of complicated systems with many degrees of freedom, the methods of statistical mechanics are accurate and especially appropriate, adequate and especially appropriate. Anyone know where that quote is from?
Which 5 minutes of puzzle?
I was about to say, is it also from Tolman?
It's also from Tolman. So just to illustrate the fact that one finds these two conceptions significantly coexisting to a degree. Just to kind of underline my point that I'm talking about kind of ideal types of how you might think about it rather than something that clearly divides any given author's position. Or perhaps I should say it does indeed divide any given author's position. It doesn't clearly divide authors into one position or another. Okay, so given I'm kind of hedging and undermining my own distinction here, why do I think this is important? Well, I'm going to go through a bunch of examples of conceptual questions that arise and get discussed in the foundations of statistical mechanics, and show how the way you think about that question ends up looking really quite different from an inferential point of view as opposed to a dynamical point of view. So, start with probability. In an inferential take on statistical mechanics, probability has to be in the theory. The whole point of the theory is it's handling my partial information about goings on, and probability is typically understood as the way in which I quantify my degree of ignorance about what the system's doing. So when I talk about my probability distribution over various phase-based states, my kind of starting point in understanding that on an inferential basis is the system has some kind of state, but I don't know what it is. The probability measure tracks that. So there's a nice piece of terminology that comes out of some of the discussions in quantum information. Who's come across the distinction between psi-epistemic and psi-ontic ideas, or between epistemic states and ontic states? It's just scattering of people. So the idea here is that taking that concept across to statistical mechanics, I've got the phase space of the system. The ontic state is the actual point in the system, which is the system's real state, but I don't know what that state is. So the epistemic state, which is some probability distribution over it, is my parameterization of the degree to which I don't know the ontic state. On a dynamical conception of statistical mechanics, there's no conceptual requirement that we have probabilities in play. There's no requirement that the dynamical laws governing collective degrees of freedom should be probabilistic. In fact, there's a prima facie suspicion that they ought not to be probabilistic because in classical statistical mechanics, the dynamical laws governing the behaviour of the microscopic degrees of freedom themselves are deterministic, or one might expect determinism in determinism out. But of course, as we all know, it seems that in the dynamical conception, we need probability to be in the picture anyway. In a Gibbsian take on statistical mechanics, we see it comes in explicitly. I should say by Gibbsian, when I say Gibbsian as understood dynamically, that means I mean by Gibbsian something very minimalist, just the idea that the way we describe systems for statistical mechanical purposes is by probability distributions. On a Boltzmannian take on statistical mechanics, it's there tacitly. The way a Gibbsian account of statistical mechanics describes the state is by of a thermodynamic system, say, is by ascribing a probability distribution. The way the Boltzmannian picture does it is by ascribing a point, but as we've seen already, the Boltzmannian picture requires various probabilistic assumptions to fill out the details. And it's also the case, I should say, that the equations we get out in either case do seem to have emergently stochastic behaviour, even if the underlying dynamics is deterministic. Okay, and notice from the inferentialist point of view, understanding what these probabilities are is tolerably clear. it's not, it's problematic in various ways, and Wayne sketched out some of the ways in which it gets us into trouble, but the basic conceptual understanding of what we mean when we say the system has a state, but I put a probability measure over states, is relatively clear. One of those things is parameterizing what the world's actually like. One of them is parameterizing what I know about the world. On the dynamicist conception of probability in classical statistical mechanics, I think life is significantly more problematic. It looks as if the dynamicist conception needs a notion of probability which is an objective fact about the system. And it's hard, not impossible, but difficult to get a grip on how that can work. It's one thing to say in the presence of stochastic dynamics, that the physics somehow it's only known probabilistically what the system will do next given its current state. There's an objective fact about the probability that its next state will be, say, decayed or undecayed. It's another thing to say of a system which by assumption has an actual state, but notwithstanding that it is objectively a physical fact about that system that it has a certain probability distribution over states. Okay, that was example 2. Example 2, think about equilibrium, the concept of what we mean by equilibrium on these setups. So, at least on one very prominent line coming out of the inferentialist idea, and given particularly clear voice in the work of James, what we mean when we say on the inferentialist take that a system is at equilibrium is that it's the state of maximum ignorance of the system compatible with the gross constraints on the system. So something like compatible with the energy the system has, compatible with the size of the box the system is in, compatible with the number of particles in the box. So to say of a system that it is equilibrium for an inferentialist, at least of James's stripe, is to say all I know about the system is its size, the number of particles in it, its average energy or its actual energy or something like that. And so to say of a system is equilibrium is to say something about my knowledge of the system, not about the system itself. So for instance, in James's framework, the way we understand the canonical distribution is to say, if I know nothing about a system, then I need to, my level of information, other than it has certain constraints governing it, then my level of information about the system should be at a minimum, conditional with those constraints. James motivates the idea that we have a certain information theoretic measure of what level of ignorance is implied by a given probability distribution, and you can derive the canonical distribution very quickly and cleanly as that probability distribution which maximizes this measure of ignorance, which conditional on the expected energy having the value it has, and that just gets you out the canonical distribution very quickly. On the dynamical conception, equilibrium is completely different. Equilibrium is the state the systems actually get into if you leave them long enough. So to say of a system as equilibrium is to say something about that system. Quite what we want to say about the system is going to depend a little on the details, but it might be, for instance, that equilibrium is the state the system gets into such that the rates of change of its various macro level parameters are 0 over a long period of time, or something like that. So the notion of equilibration in that case has a radically different character on an inferentialist than a dynamicist take on the theory. The inferentialist, to say a system is equilibrating, is saying I know less and less about it. I'm losing information about it. If I take a system that wasn't at equilibrium and I come back later and it's at equilibrium, then on the inferentialist take, that's a roundabout way of saying I start off by knowing quite a lot about the system other than its gross constraints, but I've lost all that information and all I know now is the gross constraints. On the dynamicist take, it's actual quantitative dynamical process. The system has physically evolved, the states of its collective degrees of freedom have evolved, presumably under some equations that we want to seek out, and they've reached the equilibrium state. Third example. Think about entropy and the second law of thermodynamics, which often tends to be the kind of lodestone of what's required of an interpretation of statistical mechanics or an understanding of statistical mechanics. So, on the inferentialist take, again, at least on the kind of line that's come out of the work of James, then thermodynamic entropy, which is going to be identified as the Gibbs entropy function, is to be understood as the negative of that measure of information I was discussing earlier. Or put another way, James tries to motivate and make plausible, following a bunch of work coming from inter alia, Shannon and others, that somehow the amount of information I have about a system which I'm describing with a certain probability measure is the Gibbs entropy of that measure. And thermodynamic entropy is to be in some relevant sense on which, as Jos was pointing out, Gibbs was fairly careful, Jane's going to be less so, is to be somehow identified with that. So for instance, Wayne alluded to this, Jane's has a kind of sketch derivation of the second law based on something about conservation of phase space volume. Any dynamical, so I start the system at equilibrium, I know nothing about it other than the its energy and its volume. I evolve that system under some Hamiltonian process. Because phase space volume is conserved, the only states of given gross constraints I can evolve that system into are ones which have a bigger phase space volume. So insofar as the phase space volume is to be supposed, along with the phase space volume pattern of the constraints is supposed to be picked up as the entropy, I've explained a principle that says this entropy can only go up. Of course, there's an issue there because the entropy of the actual distribution I get when I map a system about which I know nothing into some new parameters hasn't changed because phase space volume is conserved. So in some sense, to make sense of this kind of understanding of the second law that Jane's is suggesting, it looks as if we need to have some idea that I let the system evolve in this way and then I forget all the stuff I know about it other than the gross constraints. And so it's difficult to see on that line how to think about the second law as not telling us something, again, about our loss of information about a system rather than something about the system's state itself. And it's difficult not to construe the second law in general, as the decrease of entropy in general, as being some condition about the fact that I tend to lose information about systems. For the nanosystem, thermodynamic entropy had better be a property of the actual physical system. It had better be the case that when I say the system has entropy blah, I'm saying something physical about the system itself. What is that? Well, this is going to now depend on one's preferred way of thinking about the theory, but canons on the table, one might say, look, I'll carry on using the Gibbs entropy, or the coarse-grained Gibbs entropy, as my understanding of physical entropy, but I'll need to understand that it therefore is in some sense a probabilistic property of the system that depends on this probability measure, which I'm already committed to regarding as in some sense an objective thing about the system. In my view, we don't think that's satisfactory. We might think that we think entropy actually has to be a categorical property of the system, and that every given phase space point is then determining unique entropy. And if we like that kind of approach, we're likely to find the Boltzmann entropy fairly attractive. I'll have quite a bit more to say about these issues in the second part of the lecture. Okay, final example of the dichotomy I'm playing with here. Think about retrodiction and time asymmetry from the inferentialist and analysis point of view. So here's the problem for the inferentialist. I'm worried about having some kind of epistemic paradox. I've reasoned my way to thinking that it's reasonable enough when predicting what a system does running into the future to use something like a fairly even or smooth probability distribution over the system. Maybe I've rationalized that by saying I don't really know anything about the system other than its gross constraints. Maybe not, in any case. I can see that evolving that thing forward seems to be behaving in the kind of ways I want it to do. But because the underlying dynamics is time reversal symmetric, and because the property of being a smooth probability distribution doesn't seem to bring in a temporal asymmetry either, it looks to me as if evolving that state backwards in time gives disastrously bad retrodictions. And I can worry, in fact, that in some sense it undermines my epistemic warrant for my earlier knowledge in the first place, because it seems to say that I should put extremely low credence in the very experiments that gave me grounds to buy the theory in the first place. And I think a lot of the attempts to understand the asymmetry of time and the retrodiction paradox from the point of view of inferential approaches to statistical mechanics tend to be looking for, because they construe an epistemic problem, to look for an epistemic asymmetry somewhere. So maybe, for instance, the asymmetry is to be understood in the fact that I have memories of the past but not the future, that I have a lot of other information about the past beyond the dynamical predictions, but nothing at all about the future beyond the dynamical predictions. Maybe it's something more instrumentalist versions of this kind of story. Maybe it's something about the way in which I intervene in systems has a certain asymmetry. So it's all about the fact that I prepare a system in a certain state, and before the preparation point, I know nothing about. I can't treat it as isolated, and so the asymmetry comes in there. There's various moves of that kind that one might be inclined to try. On the dynamical take, I think it has a slightly different structure. On the dynamical take, I'm supposed to be making some kind of physical assumption about the system which delivers me entropy increasing dynamics into the future. If that assumption also delivers me entropy increasing dynamics into the past, and if that assumption is supposed to be true at all times, it's just a mathematical impossibility that this can all be the case. So from the dynamical point of view, the retrodiction problem isn't to be thought about as a kind of epistemic paradox. It's just a flat contradiction. There's just some flat contradiction in the different physical assumptions we're making, and one of them is going to have to go. And so where we normally try to do that is we need somehow to put an asymmetry into the physical description of the goings-on. So maybe we do that, as David was telling us about, by some kind of constraint that, by virtue of being a constraint on the initial state and not the final state, is time asymmetric. Maybe we do it, but maybe that constraint is some kind of low entropy requirement, maybe that constraint is some kind of micro-probability requirement, maybe it's both. Alternately, we could look for explicit time asymmetry and dynamics. So moves of this kind we can make. They have in common that what we're doing is putting physically understood constraints on the laws or the states or both. Okay, so let me just quickly take stock of where that potentially leaves us if we were thinking, okay, how do these kind of ways of thinking about dynamics stack up? And this is obviously the kind of view from 30,000 feet, but here's my kind of two-sentence summary of where the really deep problems lie, for various positions here. The most severe problem I think you see that you run into on this kind of story from a dynamical point of view is to understand what we mean by probabilities. This isn't the moment to say there aren't a whole bunch of other problems, and there's always something somewhat arbitrary about picking points out, but I think in each case these are worth picking out and drawing attention to. So for the dynamicist, probability is deeply mysterious in classical statistical mechanics. It's deeply mysterious how it is that a system whose dynamics are perfectly deterministic and which has an actual state can be said in any relevant sense to have a probability of being in various states, except insofar as that quantifies arguments. It's moderately hard even to explain what we mean by a probability distribution over classical states of that kind, except by virtue of something about arguments. Inferentialists are just fine with probability. It's no more problematic for them than general accounts of how probability is to be plugged into an inferential framework that we have coming out of epistemology more generally. Where inferentialists have a difficulty, I think, is in objectivity. An awful lot of statistical mechanics starts being a matter of our information about systems, our knowledge of systems, our predictive ability to know what's going on, rather than facts about the system itself. Now, it's fair enough to say, well, yeah, duh, we did say it was an inferentialist conception, but bear in mind that what we're supposed to be having an inferentialist conception of on this way of thinking is not supposed to be physics as a whole. I'm very carefully not calling inferentialism instrumentalism or something. I mean, maybe instrumentalism you might think about it as a completely global inferentialism about everything. But the inferentialist take on stat mech has an underlying dynamics which is assumed perfectly well behaved and to be understood on dynamicist grounds. The inferentialist step is supposed to be handling my partial information about that underlying dynamics and the underlying state. So the objectivity problem, I think, is not that we have a kind of our information about system-based understanding of some part of the theory. It's that understanding seems to go awfully wide. It seems to be the case that all sorts of things that look an awful lot like objective regularities in the world, like the melting of ice cubes and the fact that suns radiate and don't contract, and the passing of youth and passage of time and so on, these all seem to be very objective things that seem awkward and odd to be things that we incorporate into a framework as coming out of my partial information about situations, rather than coming out of something objective about the world. As with the probabilistic case, the dynamicist seems awkward, looks hard, looks odd, is in no way meant to mean that there aren't projects to get around that. It is to say that prima facie, that's a difficult situation here. It's not particularly difficult, modulo the kind of projects go through, for a dynamicist, as in there are a whole bunch of technical things that need to be done, but the idea that one would be able to incorporate an asymmetry into this framework is relatively straightforward. It's going in as an assumption about the dynamics, or as an assumption about the state, and that assumption is just to have a direct physical significance. It's just a claim about the way the world is, an objectively probabilistic or a categorical claim. So modulo being able to carry through those projects, the dynamicist is in a better situation on the issue of objectivity. And modulo being able to carry through these projects X is actually, I think, the other important distinction that you can draw from a kind of 30,000-foot view between inferentialist and dynamicist takes on the subject. There's an awful lot more technical work to do, typically, on dynamicist as against inferentialist routes to understanding these topics, other things being equal. Something like why systems equilibrate is perhaps a classic example of this. It's one of the main lines that contemporary physicists defending why they like the Jamesian approach to statistical mechanics will flag, is that it makes the understanding of something like equilibration enormously easier. Once you understand that why systems are at equilibrium is simply to be understood as making a statement about our lack of knowledge of the system, I can get rid of an enormous amount of really difficult technical maths about how systems are supposed to make their way towards equilibrium. I can stop faffing around with ergodicity and Boltzmann equations and one-league projections and all of this crap, and I can just say, here is a 3-line Lagrange multiplier calculation that gets out the canonical distribution.
But isn't an inferentialist going to, I don't understand, if an inferentialist is asked more detailed questions, like what expectations should I have about relaxation times, about what how observations of systems en route to equilibrium are going to come out? Aren't all those problems going to re-arise?
Yeah, and another way of putting that is that I think the price for all of that is it's very hard to get out of the idea that to understand the quantitative science of non-equilibrium dynamics. I mean, it's not that James and people since then haven't made attempts to do that. None of that I found terribly persuasive, but it's certainly a prima facie difficulty there. That's the flip side. I mean, more generally, I think, almost everyone probably knows Russell's quote about a given strategy of philosophy of maths having all the virtues of theft over honest toil. And you'll sometimes find people in, you might do texts in set theory who will embrace that and say, yeah, but look, just by stealing Zermelo-Frenkel set theory, look how much we've done with it. So you can call that moral in either direction. Okay, now, if classical mechanics were true, then I wouldn't be standing here because matter isn't stable under classical physics, and in general, claims that begin if classical mechanics were true, then X should be treated with caution for that reason. But if classical mechanics were true and per impossibile I was still standing here, then I'd probably stop at this point and say something like, okay, what we should draw from this is that the distinction between inferentialist and dynamicist ways of thinking about a given project in statistical mechanics is a helpful way to understand some of the disagreements that are present often at quite a deep level in discussions of this, and that if you're seeing conversations between people about the foundations of statistical mechanics that seem to be talking right past each other, often it can be because there's a kind of tacit commitment on one part to an inferentialist conception of the subject, and on the other party to a dynamicist conception of the subject. However, classical mechanics isn't true, and I want to see how some of this shifts over and moves if we start thinking about the case of quantum mechanics as another kind of test bed of that inferentialist versus dynamicist distinction that I'm exploring. So suppose And we basically talked almost entirely so far about classical dynamics in this setup. Is anyone not familiar with the kind of basic mathematical structure of quantum mechanics? Just a starting point. I'm not going to assume a lot, but just okay. So I won't stop in my full detail, but feel free to ask and version it. So here's a way one might think about the relation between classical and quantum mechanics. One might think, well, look, the way classical mechanics works is something like this. I have a space of possible states, phase space, where the states are points in the phase space, and I have dynamics, Hamiltonian equations on phase space, and I have rules about making composite systems. The state space of a composite system is going to be just the direct Cartesian product of the state spaces of the individual systems. Cartesian product of the category of manifolds, if you want to. And it's very natural to draw a kind of a set of direct analogies there between classical and quantum dynamics. We could say, look, for the phase space points in phase space, we have the rays in Hilbert space. So I have a certain vector space for quantum mechanics, which is supposed to be the state space. The states are supposed to be something like normalized unit-length vectors in state space, or if we're feeling slightly more careful, something like equivalence class of such vectors up to phase transformations. And just as classical mechanics has Hamilton's equations to tell us what the dynamical trajectory is through any given phase space point to other phase space points, so quantum mechanics has Schrödinger's equation, which tells us how quantum states evolve. And there is a deep disanalogy between classical and quantum mechanics, which lies in the fact that while the classical composition rule uses the direct Cartesian product, the composition rule in quantum mechanics uses the tensor product, which has the consequence that while any possible state of a classical system can be uniquely decomposed into a state of its component systems, that is generically not the case in quantum mechanics. The fact that that's possible lies at the root of entanglement. You can make a pretty good case that it's entanglement and not superposition that really drives the weirdness of quantum mechanics. Waves are like Hurl, the superposition principle approximately. So that's one way we could think about the classical quantum relationship. And people are probably fairly familiar with that. It's not the only way you might think about it, though. Here's a different way you might draw the analogy. You could say that the relation is the hold between a ray in Hilbert space and a probability distribution on phase space. And you could say that the dynamical relation holds between not Hamilton's equation for phase space points in the Schrödinger equation, but Liouville's equation for probability distributions on phase space and the Schrödinger equation. And at that point, you'd find, indeed, that the difference in the rules for composition becomes a little bit subtler, that in both cases, the state space of the combined system is the tensor product of the state space of the individual systems. And then in both cases, a state can't generically be decomposed into states of component systems. And the reason you might, yeah.
Oh, I was just going to ask, and if we did think of it this way, does this commit us to either the inferential or dynamic conception of theories if we were to do this, or is it kind of combined?
I think so far not entirely, and there's a degree of cross-classification, but you're right to flag that because I think it speaks to it to a significant extent. Okay, but the reason we might be ambivalent about which of these ways to think about the classical quantum relation is something like this. The quantum state, from a kind of naive starting point of view, sometimes seems to enter into our theories in the kind of way we find characteristic of the physical state of something like a phase space point, and sometimes in a way that seems characteristic of probability distributions in the way we see we find for something like a phase space probability distribution. So let me spell that out a little bit. On the physical way of thinking about things, if I think about a quantum state as describing the actual physical state of some underlying goings on, then that's the really natural way in which we think about microscopic goings on in physics. We talk about the state of an excited atom or something like that. We talk about the ability to propel pair atoms in certain states. We talk about their transitions between energy levels. We talk about interference between quantum systems undergoing this dynamical trajectory and this dynamical trajectory. And to a significant extent, we find it tricky to talk about entanglement without helping ourselves to these kind of ideas. I mean, that's incredibly vivid if you think about something like the scanning tunning microscope pictures we were seeing earlier of individual atoms. I mean, it's very hard to hold on to the idea that states of atoms aren't somehow telling us something objective about the system. Having said which, the probabilistic way of thinking about quantum states seems awfully natural when you start running into the quantum states of macroscopic systems. We know, because of the superposition principle, that if alpha is a possible state for a quantum system and beta is a possible state for a quantum system, then 1 over root 2 alpha plus beta is also a possible state for a quantum system. And if alpha is the state that's supposed to be representing a live cat, and if beta is the state that's supposed to be representing a dead cat, then 1 over root 2 alpha plus beta looks pretty problematic from the point of view of understanding the state physically. Whereas from a probabilistic interpretation of what's going on, states like that aren't problematic at all. It's not difficult to suppose, from that kind of understanding, that the states that are superpositions of dead cats and live cats are just ways of telling us if the cat is alive or it's dead. There's a probability of being alive and there's a probability of being dead. So, and what you'll find if you look at textbook discussions of quantum mechanics, once you get out of their very careful, very hedged, here are the axioms chapter, is that one tends fairly casually to adopt the former kind of conception of a quantum state when describing microscopic goings on, and the latter conception of a quantum state when describing measurement goings on and macroscopic goings on. And just as a kind of, while this isn't a lecture on the foundations of quantum mechanics, and so I won't fill in the details of a lot of what I'll say here, it's pretty well known that trying to take the probabilistic take on the quantum state is a challenging task at the microscopic level. I'll come back to that in a moment, but as the kind of quick one-line way of seeing why that is, interference phenomena are very, very difficult to understand on any probabilistic sense of the quantum state. So a very direct, naive sense of the quantum state, which just says superpositions of probability mixtures, can't handle the constructive and destructive interference that's characteristic of quantum mechanics. Okay, where am I going? Here is an inferential conception of quantum mechanics. Quantum states are indeed probabilistic. Why are they probabilistic? Because they are epistemic. What do I mean by that? The job of quantum states, like the job of phase-space probability distributions on the inferentialist conception of statistical mechanics, is to help us predict something. It's to tell us something about a system about which we assume to have imperfect knowledge. What is it? You see what I slide here? Yes. Here's the issue. What is it that these probabilities are supposed to be probabilities of on this inferentialist conception of quantum mechanics? In the inferentialist conception of statistical mechanics, it was dead easy. The probabilities were the probabilities of the system actually having a particular phase-space state. The distinction between the ontic and epistemic state was completely clear to us. The epistemic state was the probability distribution. What was the epistemology about that required an epistemic state? It was about what the underlying ontic state was, the individual microstate. We could try that strategy in the quantum case too. People have tried that strategy. It's got quite a lot of discussion, more in the physics and philosophy literature, but in foundational discussions in the last 10 or 20 years, particularly in quantum information. The awfully tempting choice, right back to Einstein, is to say, well, just as I've got classical microdynamics, which is the ontic theory, classical probability dynamics being the epistemic theory, so if quantum mechanics is supposed to be the epistemic theory, then there's an unknown theory we don't have yet, which is the ontic theory underlying quantum mechanics, which is to classical probability, to quantum mechanics, what classical microdynamics is to classical probability dynamics. And over the last 80 years, there's been good news and bad news on that project. The good news is that we've made a very, very large amount of progress. The bad news is that the progress has been entirely negative. We have made an enormous amount of progress in pinning down the sheer multiplicity of pathologies and problems that come about for any such theory. We already knew it was going to run into problems with relativity. Perhaps that's the least of our worries. We know it's going to have to be contextual from Koch and Becker. We know since the quite recent results of Matt Pusey and co-workers that it's got to obey some downright conspiratorial constraints on how you combine systems together. It's not quite, I think, at the level you can say this is completely impossible, but it's near as damn it. Terry Rudolph gave a talk in Oxford about this about 6 months ago, and his list of possibilities for epistemic take on the theory included several he thought were unacceptable for different reasons, the natural take which he regarded as being ruled out by the PBR theorem, and a kind of line which he wrote question mark, question mark, question mark, question mark, question mark, question mark. Very difficult to know how those programs will be taken any further. It was pretty damn hard anyway. I think you can think about these results as more nails in the coffin rather than something that profoundly changed our starting point. Okay, what's the alternative to thinking of the probabilities that way? We could think about them as measurement outcomes, as probabilities over measurement outcomes. We could say, what ignorance does the quantum state quantify? It quantifies my ignorance about what actual outcome will occur from a measurement. There's no problem building theories of that kind. In fact, there are some quite natural and moderately suggestive results to the effect that a quantum state, or the natural mixed state generalization of the quantum state, is the unique way to characterize a probability measure over the space of possible quantum mechanical measurements. On the other hand, the approach at that point is very, very close to instrumentalism. Some advocates of inferentialist takes on quantum mechanics of this kind embrace that. Asher Perez just shrugs and says, sure, it would have been nice to have an objective, realist description of the world, but quantum mechanics tells us it's not going to happen, deal with it. People like Chris Fuchs have tried to argue that somehow we can understand the quantum state as simply being epistemic over experiment outcomes, but somehow there is still an underlying reality on which we can get a handle in some indirect fashion. That position is, to be charitable, obscure. I should say that for these kind of conceptual tangles, inferentialist approaches to quantum mechanics are quite rarely discussed in a lot of contemporary philosophy of physics, to the point at which one could be almost unaware that they're out there. It's perhaps just worth being aware as a general comment on the sociology of the discipline that in physics, a lot of people still find these kind of approaches attractive, and you can see this as, if you like, the latest step of intellectual history that I guess goes back to some of the various conflicting strands coming out of Bohr's and Heisenberg's work. How does a dynamical conception of quantum mechanics go? Well, at the fundamental level, the quantum state is supposed to represent a system's physical state. To borrow that ontic epistemic language from before, the quantum state is supposed to be an ontic state on this kind of conception. Hence, psi-ontic gets used in the literature as a description of states of this kind to be distinguished from psi-epistemic. Chris Fuchs has this beautifully cruel description of people who have a physical conception of the quantum state. He says that they are psi-ontologists. Okay, and of course that take on the quantum state perfectly happily handles the first half of the problem. That handles the microscopic stuff perfectly well. It runs us into big problems in that regime where the quantum state seems to be most naturally treated as probabilistic. Where can one go in their dynamical conception? Well, we know a lot technically. We know that emergently, at the mathematical and structural level, the quantum state has the structure of something probabilistic in various regimes. We get at this via the theory of decoherence. I'll come back to this point later, but the relation between decoherence and the kind of emergent macroscopic dynamics we've been discussing in a lot of this meeting is, at the worst, a very close analogy, and at the best, pretty much an overlap. And we know a lot about it at a technical level. We can reasonably ask, is it sufficient to find that the quantum state emergently, structurally starts looking like a probability distribution in macro regimes? Well, there are various answers we could give. The Everett interpretation says yes. That's one answer. A lot of people say no, getting something that's structured like probability is not probability, and it's not possible to parley it up to probability without adding something else. Maybe the something else is additional hidden variables, not in the psi-ontology versus psi-epistemic state, but as in additional ontology on top of the quantum state. Maybe the added thing is some kind of modification of the dynamics, so that somehow all but one of the various terms in a superposition, after the point at which it's already behaving in a kind of emergent probabilistic way, vanishes, and the real probabilities are matched up with the emergent structural probabilities in the right way. I guess the most common answer that tends to be given in the physics literature among people who are advocates of, explicit or tacit advocates of dynamical approaches is probably more like this. Calculating. Have people heard the shut up and calculate phrase? Yeah. So the thing to bear in mind, if anyone mentions that, by the way, is to run the shut up and calculate interpretation, there are two requirements to be inherent to this interpretation. One is you have to calculate, and the other is you have to shut up. What you often find in people who say that they're advocates of the shut up and calculate is they don't accept the shut up part of it. As in shut up and calculate as a commitment to say, I'm not going to worry about the measurement problem, I'm going to get on with doing calculational work, is entirely fine. Parlaying that up into saying, and therefore that's an interpretation of quantum mechanics, and other interpretations of quantum mechanics are unnecessary, is a different move. But I digress. Maybe take stock of how we think about quantum mechanics from this kind of distinction, and kind of compare the situation we find ourselves in, inferential versus dynamical, in the case of quantum theory, as opposed to the case of classical static. Here are some claims. This is now moderately controversial in places. The objectivity problem for inferentialism is a lot more serious in quantum mechanics than it is in classical statistical mechanics. Why is that? Well, because in classical statistical mechanics, it was clear what we were allowed to be objective about if we were inferentialists about statistical mechanics. We were allowed to be objective about the underlying classical microdynamics, and the thing about which we were ignorant, and the thing the thing that we were trying to parameterize our ignorance over, was the classical microstate and the classical microdynamics. But quantum mechanics is the dynamical framework for basically everything. With the partial and contentious exception of gravity, then all of our current dynamical theories are taken to be either quantum mechanical or emergent classical limits of quantum mechanical systems. It's the framework in which we write all of our fundamental physics these days. So if that framework as a whole is to be deemed somehow an inferentialist framework, then there's almost nothing left for us to get a grip on and regard as the thing about which we're ignorant. And instrumentalism looms very large. But people who run ideas of this kind are often quite sunny about the prospects. They'll often say, look, every problem is an opportunity. This is exactly why quantum mechanics is teaching us incredibly deep things about the nature of the world and the nature of reality. And somehow we'll get deep philosophical insights out of it. As a rule, you tend to find that people who think will get deep philosophical insights out of quantum mechanics are physicists, and the people who think that quantum mechanics points to the need for new physics are philosophers. Make of that what you will. What about dynamicism? Well, claim the problem of probability is somewhat better in quantum mechanics than in classical statistical mechanics. Why do I say that? Well, for the following reason. No classical microstate can by itself and without probabilistic input into a theory of some kind develop probabilistically describable behavior. No classical states dynamics induces a probability distribution over macroscopically derived goings-on, which has anything other than 0 or 1 as the probability ascribes to any given output. In quantum mechanics, a given quantum state can perfectly happily, and generically will perfectly happily, evolve into states which, structurally speaking, look like probability distributions over a great many macroscopic goings-on. David Albert was putting this nicely in conversation with me a day or so ago. Think about this, if you like, from the point of view of partitions of the state space. What a macroscopic history of a classical system might be is something like, at time 1 it was in this element of the partition, at time 2 it was in this element of the partition, at time 3 it was in this element of the partition. And what a probabilistic microdynamics ought to do is it says, well, somehow given that the system is in this this macro state at time t1, this is its probability of being in this macro state at time t2. No amount of classical microdynamics will ever give that, except in the trivial 1-0 case for any given classical trajectory. I can get it out by putting probability measures down. I can get it out in a really very robust way by putting probability measures down. In other words, I can see that the dynamics I get out can be very independent of the details of the probability. It has to go into somewhere. In quantum mechanics, the nearest you can get to a classical partition of phase space like that is you can say, I'll have projectors onto certain macro states. So they're all states in projector 1, they're projected onto by projector 1 are states of such and such temperature and pressure. All the states projected onto by projector 2 are states of such and such temperature and pressure, and so on. But in quantum mechanics, of course, a complete set of projectors of this kind is not such that any given state will lie in one of those projectors. In fact, a set of measure 0 states lies in one of those projectors. And very generically, quantum mechanical pure states evolve into superpositions of many macrostates, and the amplitudes of those superpositions when mod squared behave a lot like probabilities. Whether that's enough is contentious. Maybe it's only enough. Maybe it's only okay for referentials.
Could you remind me what the problem of probability was?
How we understand how the theory can have probabilities coming into it. How we can put probabilities into the theory.
Not what there are probabilities of.
You can regard that as part of the problem.
Is that not part also of the problem of objectivity?
Put it this way, it might be that the problem of objectivity has got so bad in quantum mechanics that the problem of probability is still looming for the inferentialist there as well. But I take it that insofar as the inferentialist has a story to tell about what they're supposed to be ignorant of, whether it's some underlying very kooky microdynamics or the outcome of measurements, then understanding further why that ignorance is quantified by probability is not going to be especially problematic. So you just take a fairly kind of Chris Fuchs style take of this, then the probability, what the theory is objective about is supposed to be the outcomes of measurements. What's my inferential activity? It's my ignorance of what measurements are going to result. Why do I get probabilities now? Well, on relatively standard Bayesian grounds. Why do I represent them by a quantum state? Gleason's theorem.
I was thinking particularly of the distinction that even if you have a tensor product structure for distributions of a classical state spaces for composite systems, it's still only a subset, it's a compact subset, and I think it's fair to say that in that case there's always a unique decomposition of such things into pure states.
In classical physics,
in the classical case.
Yeah, that sounds right.
In the quantum case, it doesn't matter whether you use pure states or mixed states.
Yeah.
If you have an entangled state, there are various decompositions into sums of products states.
Yeah.
And so in the quantum case, you have this what is usually called preferred basis problem. You don't know. If you've got probabilities, you can say what their probabilities are. You have to introduce a preferred basis. That does not arise in classical.
Sure.
So I'm not quite sure now whether that's part of the problem of objectivity or problem of
I think for the
I think it's certainly one aspect in which quantum mechanics is worse off.
Well, bear in mind, I mean, it's going to depend for who. I mean, for the inferentialist, I mean, in a sense, I'll come and say more about density operators in a minute, but just the quick kind of one-line move. For pretty much any advocate of an inferentialist position I know, there's no very interesting distinction to draw between pure and mixed states, and the interpretation of a mixed state as a probability distribution over pure states is entirely discarded.
Yes, but the problem of a preferred basis is that.
Well, if you are, you have to think what kind of inferentialist position are we thinking of. We're thinking about something where I'm what I make inferences about is the outcomes of measurements. Then I've just got no problem at all. I mean, I just for any given measurement, whether on a composite system or not, is represented by some self-adjoint operator or some PDM, say, some family of projectors. And the quantum state determines uniquely and well-definedly a probability distribution there. If I think it's a probability measure, it's somehow the quantum state is very indirectly coding some kind of ignorance interpreted probability measure over some deep and mysterious underlying microdynamics, then frankly at that point the preferred basis problem is very much the least of your worries, because we know by now that the structure of that theory has to be so opaque and alien and conspiratorial that what it looks like in the kind of system decomposition we see in quantum mechanics is going to be completely unpredictable. I mean, I think these results are bordering on no-go theorems, to be honest, but at the very least they tell us that the theory is wildly interconnected, vastly more so than even quantum entanglement suggests, in a way that's very hard to kind of make clean sense of. Yeah.
Just to clarify a bit, this problem of the probability for the dynamical conception,
yeah.
That given that as we remarked in the question, they are not really compatible, the inferential conception and the dynamical, cannot one that is seeking a dynamical conception of physics, that is seeking the laws and the dynamical evolution independently anyway when it's faced with the need to appeal to a probability, just simply make as the inferential conception and take it as an epistemic thing. So in classical mechanics.
You're talking about quantum mechanics here?
Classical.
Oh, my claim is that, well, it goes back to my kind of ideal types thing, if you like. Is there logical space to say, I'll have a program which will take the best bits of the dynamicist strategy and thus avoid the dynamicist problem of probability, and the best bits of the other way around. I'll take the best bit of the inferential strategy and avoid the dynamical problem of probability. I'll take the best bit of the dynamicist strategy and avoid the worries of relativity. Is there logical space for that? Absolutely, but that's the beginning of a research project rather than an ending of the problem. I think it's not terribly relevant to report it because I think the situation is too transformed in quantum mechanics, but to some extent that goes back to Wayne's issue of whether we ought to be looking for an autonomous understanding of classical dynamics anyway. Okay, so the last thing I want to do on this half of the lecture, and I'll take a break after this, is see, okay, what happens when we start just beginning to explore how a quantum mechanical version of statistical mechanics looks. So far we've looked at the division I've drawn in classical statistical mechanics and in quantum mechanics, and now I want to look at quantum statistical mechanics. And of course, in a sense, since nobody thinks that classical dynamics are the right dynamics, at some point we have to engage with quantum statistical mechanics, and classical statistical mechanics is at most a kind of important step along the road to solving that problem. So, let me see where I'm going with this. Yeah. Okay, so thinking about quantum statistical mechanics. What you might naturally think is that you'd like to try and run the same line of thought that we ran in classical statistical mechanics. In other words, we get classical statistical mechanics from classical mechanics by putting a probability distribution over the classical state space. So it's kind of tempting to say, well, the way we get quantum statistical mechanics is likewise going to be that we put a probability distribution over the quantum state space, so that we say, for every given quantum pure state psi, the probability of that state, of the system state being psi, is blah. And then we just bring the, we just apply whatever our preferred classical statistical mechanical understanding of the probabilities is to those probabilities, mutatis mutandis, and basically our whole interpretive framework in classical statistical mechanics gets carried over. And from that point of view, in principle, you'd have lots of combinations of these kind of views in play. However, I don't think it's as simple as that. If we start off by thinking about the inferential conception of quantum mechanics, so on that conception, the quantum state is a probability distribution over something. And to be to be ignorant of what that is effectively a second order probability distribution. It's a credence function over credence functions insofar as it's anything at all. And it's not really clear even how to make sense of that. And certainly in terms of application of it, the distinction just drops away entirely. And I'm left with the idea that the whole thing just kind of collapses down. Probabilities. Yeah, sorry.
Just a technical question.
Yeah.
Probability distributions of probability distributions are just probability distributions, right?
Mathematically, exactly. That's what I mean by collapses down.
Oh, okay.
So, but there are circumstances where we still think that the distinction between the two chunks of that makes conceptual sense, even though in application it just collapses down. I mean, a classic one would be I'm ignorant of the decay rate of the neutron, let's say, in which case the probability I give to the neutron decay in the next 10 seconds is going to be a weighted sum of the probabilities I would be giving it conditional on a given hypothesis about its decay rate. And I assume the decay rate is the objective probability. And so there, even though I can just multiply those together and get one probability, it makes sense to understand the division. Claim, if I have an inferential conception of quantum states, that doesn't really make sense. There are contexts in which you could talk about this, say having a credence or my having some credence, but they're weird situations of self-doubt and lack of self-knowledge and so on. There are probably situations where you can talk about me having an objective physical probability of having a certain credence, but again, that doesn't seem to be what's going on in this situation. Yeah.
Do you mean by collapsing down that it is inconsistent?
No. I mean that two-level probability collapses to a one-level probability.
But that's not to say that if I have probability distributions over psi states, that the result will be represented by the psi state.
Absolutely not. No, that's true. It won't be. But if the psi state is itself supposed to be carrying out the task of representing a probability distribution, then the overall probability distribution will just be the product of those. How it's supposed to do that job is going to depend on the details of how you tell the inferentialist story. But no, of course, you're absolutely right mathematically that probability distributions over psi states don't give the same predictions any given psi state. In fact, I'll go on to that. Thank you. Let me call the sense of the board for a second, because there's a step that makes this point even further, which is in quantum mechanics, it's already the case. Actually, let me say the relevant thing to the Dynamical story first. Hold Joss's point in mind, because it's important. We'll come back to it. So on the inferential conception, we've got a conceptual problem of why we would want an autonomous statistical mechanics of a quantum mechanics that was itself supposed to be understood inferentially. Here's the second step, and here I'll need to fill in a little bit of mathematics that's playing a role here. So suppose, who's familiar with the formalism of mixed states for quantum mechanics? Anyone not familiar with the mixed states formalism for quantum mechanics? Yeah. Sure, okay. So here's a quantum mechanical issue. I mentioned that in quantum mechanics we have entanglement. Say I've got a spin, so say there's two spin half systems, so each system has a two-dimensional vector space of pure states. I give Molly one of those systems and I keep another. There is a vector in the tensor product of those two systems which represents the joint state. And so maybe if, suppose pure states of Molly's system are states like this, and pure states of my system are states like this. But among the possible states of our joint system are going to be states like this state. And given I have access to states like these, I can take superpositions of them. And in particular, one of the possible states of our joint system could be something like this state. which is a superposition of a state where both the spin particles are up and a state where both the spin particles are down. And I hope it kind of looks intuitively plausible that no state of this form can be the product of two states of this form. Because any product I take like this is going to have cross terms. And there are no cross terms here. There are no up, down, or down, up terms here. So in general, in quantum mechanics, the state of a subsystem, the state of a combined system can't be regarded as just determined by states of its subsystems. And in fact, there's no allocation of states of this form to subsystems in a way which would allow us to correctly predict the results of any measurements carried out on Molly's system alone or on my system alone. Now, quantum mechanics could be so weird that there was no mathematical object at all that described the state of the results of measurements on Molly's system independent of mine. It could be that by making certain modifications of my system, I affected the probability of various measurements made on Molly's system, certain manipulations. Quantum mechanics isn't quite that weird. There is, in fact, a mathematical object which correctly predicts all of the measurements that could be made on Molly's system if we prepared one of these joint systems and then I threw mine in or something. And those states are called mixed states, or sometimes density operators. And mathematically, I think if I try to tell people who know what they are mathematically already know, and I can go try to tell people who don't, then I'm probably not going to remind you fast enough to take it on board, so I won't go into the details, but roughly speaking, exactly speaking, but rather fast, these mixed states are self-adjoint operators, linear operators, on the vector spaces describing the states of the individual quantum systems. And the idea of one of these mixed states, so I've got a state, suppose I've got some operator x, let's say, which represents some measurable quantity. Remember, in quantum mechanics, measurable quantities are represented by operators. In pure state quantum mechanics, if I've got some state psi, the probability, the expected value of a measurement of x given that state is psi is this guy. When I've got mixed states in play, I've got some mixed state rho there, which is an operator, and the expected value of measuring x given state rho is equal to the trace of rho x. So the mixed state framework is comes into one of the two critical places the mixed state framework comes into quantum mechanics is in the description of entangled systems. It is the most complete description available of one part of an entangled system. We still have the property that knowing the mixed state of Molly's system and knowing the mixed state of my system underdetermines the joint state of our systems. It's a kind of metaphysical question, I suppose, about whether we want to say that any system at all in entanglement really in the deep metaphysical sense has a state. But on any halfway operationalist or doing any physics with it conception, we do want to use these things as describing the state of the system. And any system that is entangled, the only thing on the table to describe its state is going to be one of these operators.
Yeah. But David, even if, and maybe I'm getting ahead of you here, and then I'll just shut up. Even if we were to grant, so I take it what you're alluding to here when you say mixed states already need to be admitted as physical states is because of these considerations of entanglement. But look, at least in very ambitious Boltzmannian style versions of statistical mechanics, what we're applying these probability distributions to are initial states of the whole universe, and there's no argument of the kind you're alluding to here that mixed states of the whole universe need to be admitted.
Yeah, agree. Can I leave on the table and park it and come back to more detail in a few minutes? But just to finish the fleshing out here. So the mixed states come into the theory in this case because of entanglement, independent of any probability situations. there is a very interesting and suggestive mathematical fact, which is that if I want to represent probabilistic mixtures of quantum mechanical pure states, then from the point of view of any measurement I might make on the system, the most general such representation is as mixed states. So for instance, if the system has probability P1 of being in state psi1, P2 of being in state psi2, dot, 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 then, let's do it here, then this state is totally efficacious as the description of what the probability is of getting any given measurement outcome if I measure a system which is in state psi I with probability pi. Now, the question of whether that's a complete physical description of what's going on is a moot point, but as a mathematical fact about the empirical content of the theory, you know everything you need to know for predictive purposes when you know that mixed state. And that rule is many to one, so a great many probability distributions over pure states give rise to the same mixed state. Okay, so that's my background about mixed states. Let me now say some stuff about why that's relevant. On the inferential conception of quantum mechanics, there's really no very interesting distinction between pure states and mixed states. They're both different ways in which I can describe probabilities to measurement outcomes. Pretty much universally as a statement of sociology, and I think more defensively than just on those grounds, advocates of inferential strategies have significantly elided the significance of the difference between mixed and pure states. That is, they've generally regarded mixed states as the most general description of my lack of information about a system, and pure states as just being a particular special case of relevance in certain experimental contexts, but of no particularly separated out metaphysical significance. So from the inferentialist point of view, here's another way of seeing how the notion of mixed states, so the notion of probability distributions over states kind of collapses away from us. If I put a probability distribution over a bunch of mixed states, then I've got, say, probability, say Q1 for mixed state psi1, Q2 for psi2, sorry, rho 2, dot, dot, dot. Then the state rho equals some Qi, rho I, is for measurement purposes a complete description of the possible goings on in that situation. So in other words, a probabilistic mixture of mixed states is just another mixed state. Notice the really sharp disanalogy here with classical mechanics. A probabilistic mixture of classical states is not, it's not anything like a classical state. So if I'm regarding mixed states in my basic dynamical starting point states, then the dynamics I'm getting is closed under adding probabilities to the theory. On the dynamical conception of quantum mechanics, it's coherent, as it wasn't on the inferential conception, to add probabilities to the theory, to have probabilities over quantum mechanical pure states, to be understood either epistemically or in some other way. However, we can ask questions about whether they're any use to us. I mean, we were driven to introduce probabilities in classical statistical mechanics, perhaps partly for very general reasons about the deep underpinning of the theory, and this links to David's comments about Boltzmann, but also and more pragmatically because of the need to make probabilistic claims about individual systems, to say the results of measurements made on them, to talk about all the various probabilistic or quasi-probabilistic properties of systems that classical StatNet was in the business of describing. Introducing probability distributions over pure states enormously increased our descriptive resources in classical statistical mechanics. Introducing probability distributions over quantum mechanical states, when we're describing the quantum mechanics of individual systems, increases our descriptive resources in quantum mechanics not at all. Because any given quantum mechanical state, particularly of the kind of big systems that we're interested in quantum mechanics, is perfectly capable, even if it's entirely isolated from the world right now, of having become thoroughly entangled in all sorts of ways with its surroundings. In fact, even requiring that it's entangled only because something happened earlier already kind of begs the question against certain attempts to understand directions of time as coming out of physics. The range of possible states that box could be in includes the full range of mixed states. Going from that set of mixed states to probability distributions over mixed states doesn't help me in the slightest in my descriptive account of what any given system is doing. So, while it's maybe too strong to say that there is no role for a probabilistic concept and for an additional statistical mechanical concept of probability, even on the dynamical conception of quantum mechanics, the role is enormously attenuated at best. The only remaining space one might have for the need of a probability distribution over pure states is in some part of the deep underlying framework of the theory. The need to put these things in just all over the place to make sense of our ordinary stat-net practice entirely goes away in quantum statistical mechanics. And in fact, you see this if you look at the uses of quantum statistical mechanics. The theory just talks about mixed states. There's no further consideration in play there. One's just doing the physics of the mixed states. So claim, either way, and modulo some of David's concerns, quantum statistical mechanics becomes quantum mechanics itself in certain regimes on certain assumptions. It's not an additional overlay onto quantum mechanics in the same way that classical statistical mechanics is an additional overlay onto classical mechanics. Okay, let me draw a few conclusions from this half and then we can take a break. Suggestion, and this will come into what I want to talk about in the second half. The main is a bit strong maybe. A major or a useful locus of a lot of the foundational disputes in a lot of bits of statistical mechanics, I think, might, particularly in those places where often it gets cached as a disagreement between Gibbsian versus Boltzmannian ways of doing statistical mechanics, might more helpfully be thought about as a kind of inferential versus dynamical division in ways of thinking about things. There's a surprisingly close parallel to that dispute in a significant part of the dispute about the interpretation of quantum mechanics. Maybe not that part was particularly visible in philosophy of quantum mechanics proper, but a big part of what happens when you start engaging with people in foundations of physics about the interpretation of quantum mechanics. Again, I'm probably overreaching slightly in claiming because of how quantum statistical mechanics works, it is much, much harder to run independent answers to those notions than you might imagine. I think there's the kind of impression you might have about quantum statistical mechanics is it just sits on quantum mechanics like classical statistical mechanics sits on classical mechanics. It's really, really hard to make that run. And that makes it really difficult to run separate answers to the inferential versus dynamical way of thinking about things across the two subjects. Yeah, David?
Can I just ask a question about the last slide? That is the previous slide. So look, so I very much see what you're saying about mixed states in the quantum case. But let me see how this works in detail.
Yeah.
I have a macroscopic description of some system. In the quantum mechanical case, just like in the classical case, in the quantum mechanical case in particular, there's going to be an enormous number of different mixed states that are compatible with that macro description. Okay. Moreover, we still know, in the same way as we did in classical mechanics, from the reversibility arguments, that some of the mixed states compatible with that macro description are going to behave perversely.
Yeah.
I mean, the argument might be different only in the following sense, but maybe this is what you have in mind. In the quantum case, as opposed to the classical case, there will be a simply specifiable mixed state, okay, that promises to get all the stuff right, whereas we can't put our finger on a single classical state, or wouldn't even know how to specify. Its specification would be extremely complicated, which is going to get everything right for us. Is that the difference? I mean, maybe I should pause after the first part of the question.
I mean, that's a route you might go.
Right.
I was trying to say something a little more tentative at this point. I mean, here's a somewhat minimal way of putting it.
Right.
And I'm really, in a sense, I'm less advancing a thesis and more kind of, in some ways this talk is less of a kind of, here's the deductive thesis and more, look at this, guys, it looks really different from what you thought.
Right, good.
But a way of putting it would be something like this. A putative starting point you might have in classical mechanics is that to get the physics right for a system that I want to evolve forward in time, I need to do something like assume a uniform distribution over its states.
Right.
And then all sorts of subtleties come out. I realise that actually I've got much more freedom than that.
Right.
I also realise that that's going to be problematic for retrodiction purposes, but that's my kind of starting thought. Now in quantum mechanics, the starting thought is simply, I better assume the system state is proportional to the identity operator. So the starting thing I need, even before I start doing my foundational undergirding in classical mechanics, looks like a probabilistic claim about the various states.
Right.
In quantum mechanics, it's a categorical claim.
Right.
That's the shape of the starting point. And then, I mean, the suggestion you're making is then an interesting place where it goes, but that's,
right.
for my purposes here, I'm defending that.
Good.
Okay, so just to finish wrapping up, this is a few sort of quick further thoughts that come out of this, none of which I'll defend in any great detail. I think there is this is not a philosophy of stat-net comment, so I'll beg Wayne's indulgence for about 20 seconds. There's, I think there are some virtues in seeing the quantum measurement problem as the problem of understanding the incoherence between these different incompatible conceptions of the quantum state going on in physics. I think often, when we think about the quantum measurement problem, we jump to the idea that the quantum state must be physical, and then interpret the measurement problem in that kind of framework. In some ways, I think that's better thought about as a first step in deciding what one's solution to the measurement problem is. And I think if you set the problem up that way in the first place, you've already lost a whole bunch of people coming in from various bits of foundations of physics who've got a very different conception of things. You'll find advocates in quantum mechanics of psi-epistemic approaches will draw a strong analogy, that is of inferential approaches in my language, to statistical mechanical ideas. And it's notable, and this is if you like, an interplay between philosophy of stat mech and philosophy of quantum mechanics, that a lot of that is presupposing a very strong reading of statistical mechanics of a particular kind that already is very aligned to their kind of take on things. So often, I think this is not, I think, a deliberate piece of trickery. I think a lot of people in physics, say, who have an inferentialist conception of stat mech have almost forgotten that there was a rival alternative on the table. The way probability seems to be coming into quantum mechanics looks really, really different from classical mechanics. So at heart of the interest in that is historical, and part of that is going to be as a setup for moving into the quantum mechanics. It's not at all clear that the continuity. This coming, I guess I'd probably put as construe my historical rather broadly, I'd also construe it as the interest in the question of seeing how classical statistical mechanics functions as an autonomous discipline. But insofar as one's task is understanding the statistical mechanical phenomena in the observed world, then one needs to be extremely cautious about the idea that one should understand the classical probability and just transfer it over. It looks like some very interesting different stuff happens when you move across. There's a caveat. Bohmian mechanics seems to need to use the undeconstructed classical statistical mechanical notion of probability. So maybe Bohmians still want to look at this stuff
for
carefully.
a different purpose.
For a different purpose,
Right,
indeed. But
right.
probability
To
is
get
the
the
same
quantum
kind.
probability.
Yeah, but
Right.
probability is the same kind of conceptual
Right,
character.
right.
And any more further thoughts? Yeah. I'll just leave that up there. I've been saying that kind of all the way through. Okay, why don't we take a break at that point? What I want to talk about in the second half is I want to go and look at the issue of Gibbs versus Boltzmann statistical mechanics, by which I don't really mean the historical accuracy of that. I mean that as it tends to get lost in the contemporary discussions of this. I want to suggest that a lot of criticisms of the Gibbsian approach that have come from advocates of the Boltzmannian approach or better to be seen as criticisms of the Gibbsian approach conceived of as an inferential strategy, and that actually it's perfectly possible to think of the Gibbsian approach to stat mech in a dynamicist way that's actually very simpatico to the ideas that people attracted to Boltzmannian statistical mechanics have in mind. So here's what I want to talk about in the second half, and the link to the first half of my talk is non-zero, but there's a certain modularity here. So one thing you find if you look at contemporary philosophy of statistical mechanics is there's a lot less consensus than there is in, say, other major areas of philosophy of physics as to what the problem is in the first place. So take an extreme example. If you look at philosophy of quantum mechanics, there's a fairly clear consensus that the heart of the subject is the measurement problem, and notwithstanding some of my quibbling earlier, there's a reasonable consensus about what the measurement problem is and how to think about it. And even if you disagree with some part of that consensus, it's clear where you're starting. So the subject of logical geography is moderately clear. The logical geography of philosophy of stat mech is a complete mess. And so people trying to kind of characterize the locuses of dispute here, particularly in kind of non-historical discussions. I think some example would be Roman Frigg's very nice kind of survey article a few years ago, looking for ways to characterize the debate, often characterized as being a kind of dispute of Gibbs versus Boltzmann. And I guess what I want to suggest is that that dispute is kind of merging together two questions. There's a question about the Gibbs versus Boltzmann formal frameworks for doing statistical mechanics, and there's a question that I guess I would roughly want to map onto my inferential versus dynamical dichotomy in the previous half of the presentation. Why do I think that matters? Well, at least in part because if you want to ask what does mainstream statistical mechanics look like, it looks an awful lot like the formalism and machinery of the Gibbsian project. I was awfully careful in my presentation on Monday to be very neutral and instrumentalist about what the predictive core of equilibrium statistical mechanics is, and I very carefully didn't say simply the assumption is that the equilibrium state is the canonical distribution, but you can see that what I said was within a very short step of that. And in general you find that the machinery of equilibrium and non-equilibrium statistical mechanics is all about the evolution of probability distributions, it's all about calculations of the Gibbs entropy, and an awful lot of machinery and formalism of this kind. And so if you're not careful, a commitment that the right way to think about statistical mechanics is, quote, Boltzmannian, whatever that is taken to mean, and that therefore, and that one should not be using the Gibbsian way of thinking, is at least in danger of committing you to having to redo all of that physics, or make sense of it again, and not just take on board that kind of existing framework. Now, in my opinion, philosophers of physics are often kind of dangerously blasé about committing themselves to requiring big chunks of mainstream physics to be redone. But at least in this case, I think it would be attractive to see if we can avoid throwing out the baby with the bathwater. So what I really want to do here is I want to kind of, starting with a pretty unquestioned dynamicist position on my earlier dichotomy, have a look at what the positions in the contemporary debate are that normally get labelled Gibbsian and Boltzmannian, and I'm not going to really connect that at all to what was historically meant by those authors. I'm going to look at the main criticisms of the Gibbsian approach that have come out of the neo-Boltzmannian tradition, and I'm thinking here in particular of criticisms that have come from people like Shelley Goldstein, Joe Leibowitz, David, Craig Callender. I want to argue that those are criticisms more of bad, or I suppose in my earlier framework, inferentialist motivations for Gibbsian statistical mechanics, rather than criticisms of the machinery of Gibbs itself. I want to show that we can make a perfectly happy sense of Gibbsian statistical mechanics on kind of background foundational assumptions very congenial to the contemporary kind of neo-Boltzmannian position that, for instance, David was sketching earlier. And in fact, I'm going to finish off that by trying to show that you can show pretty much, if you grant the dynamical assumptions that are required by that neo-Boltzmannian program, you can pretty much run the Gibbs framework and get out a Gibbs entropy that's numerically equal to the Boltzmann entropy. So that's the kind of perspectives of what I want to do. Notwithstanding my earlier worries about this, I'm going to run this debate entirely in a classical framework. Right at the end, I'll say a little bit about quantum mechanics. And my reason for doing that is pretty straightforward. It's that the debate on which I want to comment is pretty much 100% classical, so there isn't a quantum version of it to engage with. And as I say at the end of it, it's entirely a coincidence. Okay, so what I want to start off by doing is saying what I take the contemporary neo-Boltzmannian position to be and the kind of sense of Gibbsian statistical mechanics that seems to be how it's being used in contemporary physics to be. And I'm just, my understanding is that the relations between what gets called contemporary neo-Boltzmannian statistical mechanics and what Boltzmann thought are complicated and subtle, and I should be quite clear that I'm just using these as labels for these contemporary positions. Okay, so here's a way of starting off. Here are some requirements you might have on an account of statistical mechanics. You might, if you like, think that some of this is the conceptual underpinnings you require to underpin my kind of brute force shuffle and calculate recipe for Monday. We want to know how the thermodynamic systems and the macroscopic scale systems that we're studying are to be represented in the mathematics of our theory. We want to know what the mechanical correlate is supposed to be of the thermodynamic entropy. We want to know what the mechanical correlate is supposed to be of the claim that systems enter thermal equilibrium and are at thermal equilibrium. Sorry, I mixed those together. We want to know what the correlate actually is of the claim that a system is at thermal equilibrium. You know, what kind of constraint on the state of a system is being imposed there. And we want to understand what the account is of the fact that systems approach equilibrium. Now, I'm not 100% sure if I were to set up what I think should be the key foundational questions in statistical mechanics, I'd do it quite like this. This is more my reconstruction of what I take to be the project as understood in a lot of the salient literature here. But I also think this reconstruction is not far off what we should be trying to do. So here's how the open brackets, neo, close brackets, Boltzmannian version runs as I understand it. David can correct me if I mischaracterised. I partition phase space up into macrostates. Macrostates means something like these are macroscopically indistinguishable states. Exactly what they mean is a little bit open to question. How do we represent systems? Phase space points. You know, a system is a mechanical system, it's got a state. How do I represent it? Well, there's a point in phase space that tells me where all the particles actually are and how fast they're actually moving, and that's a system. What's the entropy of a system? Well, and this is hopefully all the vision for stuff that Jos and David has already shown you, that if you want to know the entropy of a system, first of all, here's phase space, here's a macrostate, work out which macrostate the system's in. It's, let's say, in this one. Work out the phase space volume, well, energy hypersurface volume of this particular macrostate, take its log, and that gives you the entropy of the microstate. So notice that entropy here is a property of individual systems, individual microstates. You know, input the actual positions and momenta of all of the particles in the coffee cup, output the entropy of the system. When a system's at equilibrium, one of these macrostates is going to be the biggest macrostate, just pretty much analytically. Non-analytically and highly importantly, for big systems, one of the macrostates is typically going to be the overwhelmingly largest macrostate. That's the equilibrium macrostate. The system is at equilibrium if it's in the equilibrium macrostate. So again, being at equilibrium is a property of individual systems as characterized by a microstate. And why do systems approach equilibrium? Well, glossing enormously something like, it's just a matter of phase-based geometry combined with reasonable assumptions about the dynamics. Those assumptions normally being things that we only prove in the kind of loose conjectural, gestural way, but one makes plausible the approach to equilibrium by pointing out the enormous disparity in volume between the equilibrium space and the rest of the space, and supposing that the dynamics, unless they're reasonably kooky, are going to kind of take you in there and basically stay there for ages. Okay, so that's hopefully all the vision. Here's a construal of the Gibbsian, or what's being called the Gibbsian approach here, along similar kind of lines. We don't represent systems by points in phase space, we represent them by probability distributions in phase space. And we often gloss those probability distributions as representing our ignorance of the true microstate. What's the entropy? At first pass, I'm going to have to be careful here, but at first pass, the entropy of the system is given by Gibbs' entropy formula. It's a function, it's a nonlinear functional of the microstate multiplied of the macrostate. Sorry, of the distribution. If the distribution is rho, integrate minus rho log rho over the whole of the phase space, and that'll return you number. Identify that with the entropy. When a system's at equilibrium, well, again on first pass, equilibrium is the state in which things don't change, so the system's at equilibrium when the rate of change of the distribution is zero. I think Wayne's point probably comes up here. What here is being called Gibbsian statistical mechanics goes significantly beyond the extremely careful position that Gibbs himself stayed to, but I think I'm more or less characterizing the way a vast bulk of kind of contemporary, not terribly foundationally switched on statistical mechanics has actually used that machinery since then. Okay, why am I being cautious on my first passes? Hopefully you all know after the last few days, but just to remind you all, under Hamiltonian dynamics, the Gibbs entropy is constant for motion. It doesn't change. So Gibbs entropy isn't going to go up. That should make us suspect that there's a problem with the approach to equilibrium. You would be right to so suspect. The equations of motion for the system we're studying here are characterized such that if the rate of change of rho is 0 at all times, it's just not going anywhere. It just must have been 0 at all times previously. These are first order dynamical equations. They've got a time reversal structure. So systems can't get into equilibrium. Equilibrium, if you like, is a kind of transcendental state. And if you read Larry Sklar's book on statistical mechanics, which spends a lot of its time in a broadly Gibbsian framework, you'll find a lot of discussion about how to characterize the unique rho dot equals naught state, and various discussions of why particular states that have rho dot equals naught have characteristics that they have. Attempts to show that the unique state satisfying rho dot equals naught is going to be the microcanonical ensemble or mixtures thereof. But then you move on to the equilibrium, the non-equilibrium part, and you realise that the big problem, and this is not a criticism of Sklar's book, he's perfectly upfront about this, the real problem of all of this is that even if you did characterise equilibrium that way, it's totally opaque how you get into equilibrium. Okay, so how does the Gibbsian approach solve that? Well, there's a whole bunch of things on the table, but most of them are not really acceptable to the dynamicist conception of how to do stat mech. The only one really on the table, I think, other than maybe modify the dynamics, that's acceptable from a dynamicist point of view is the kind of coarse graining strategy that Jos talked to us about yesterday, which goes, in my kind of reconstruction of it, something like this. I introduce a coarse graining map. I'm using the same terminology here that I use for Swansea projections. It's a linear map. It's a projection. The easiest way to think about it, the most normal one used foundationally, is I'll divide phase space into cells, and I'll replace the distribution with that distribution which is uniform across each cell and agrees with the original distribution on the probability of cells. So applying the coarse graining map leaves the probability of macrostates invariant and leaves the probability constant on each macrostate. Or each coarse grained cell, I should say. There's no commitment for them to be macrostates in this setup. There are other coarse graining maps. As some of them have that character, some of them doesn't, it kind of doesn't matter. Often, the fact that we're doing this gets glossed as saying, look, our measurements are imprecise, we don't know everything about the system, so the idea that we represent, the thing that represents what we're doing is to be understood as the actual distribution rather than some smearing of it is unrealistic. It occurs to me only even now as I speak that there's an interesting connection between that way of thinking and what Wayne was saying this morning, but I've got no further thoughts as to where that goes right now. We redefine the entropy. Coarse grained entropy of distribution rho is just the ordinary Gibbs entropy of the projected bit of rho, so it has this form. Just it's important to note the way that's a function of that thing there is still a function of the original probability distribution. The coarse grained entropy is a function of the original probability distribution worked out by first calculating the coarse graining. But it's a function of the distribution in just the same way that the function cos squared theta plus 2 cos theta plus 1 is a function of theta, even if it's a function of theta that you have to get by working out cos theta first. And now the system's equilibrium if the rate of change of the projected part of rho is 0, or near enough 0 in fact, probably. I should probably have an approximately equal to that. Okay, so understood that way, we don't have an immediate paradox. The Gibbs entropy is not a constant of the motion. Whether that's satisfactory, what the problems with that, I'm just going to leave for the moment, just put that on the table as my kind of statement of the form of Gibbsian thermodynamics, Gibbsian statistical mechanics that I'm going to engage with. I'm just starting to lose my voice, so let me just get some more water. Okay, so what are the criticisms of this kind of approach that come out of the contemporary literature? And I'm going to simplify in very substantially. I'm drawing probably more than anything else on David's book and also on Craig Callender's work, in particular Callender's paper taking thermodynamics too seriously. This paper, I'm probably in fact drawing on the whole lot. Anyway. So, simplifying rather, I think, here's the shape of the objections that come up. There's a concern that the approach is too subjective, that somehow it's not allowing for the objectivity of thermodynamics or the approach to equilibrium. And you see then in particular there's a concern that the notion of probability here, as cashing out our ignorance of the true microstate, is confusing the state of a system with my state of knowledge of the system. And there's a concern that the introduction of the coarse graining, justified in the way it is, somehow makes an objective fact about systems, e.g. that they approach equilibrium, depend on something that should be external to that, how actually I can measure and engage with the system. Secondly, there's a worry that entropy, thermodynamic entropy, had better be a property of individual systems. If the entropy of this water is supposed to explain how it's supposed to parameterize in various ways how much work I can get out of this water in certain ways, it better be a property of this water. So the entropy function, says the neo-Boltzmannian, needs to be a function of state. And it shouldn't therefore be a function of a distribution. Particularly shouldn't be a nonlinear function of a distribution that can't even be understood as an expectation value. And there's a worry, this is almost like what you might call a judo move, if you like. There's a worry, and particularly comes in Callender's work, that the Gibbsian approach is being defended in part, sometimes explicitly and sometimes tacitly, as having as an advantage over the Boltzmannian approach that it can somehow avoid what concerns about Poincare recurrence because distributions don't occur, and somehow give us a notion of a second law that is exceptionless. Maybe even give us a notion, but by the use of the coarse graining, it can give us an understanding of a genuine time asymmetric dynamics without any further change of the microdynamics. Says the neo-Boltzmannian with a great deal of justice, this is nuts, the microdynamics actually has recurrence in it, real systems, insofar as they're described by the microdynamics perfectly, will in fact recur, if your theory says they don't, so much for your theory. Sorry, I should say when I say theory, I don't mean the real world has the recurrence, I mean your lower level theory has the recurrence, so if your higher level theory doesn't have it, your higher level theory can't be said to be supervening to whatever net sense of your lower level theory. Okay, so yeah.
Just on the second point, the worry that on the Boltzmannian view, you can understand how the entropy of bottled water depends just on the state of that system, whereas in the Gibbsian account you can't. I mean, that's only true for the Boltzmannian account given some particular partitioning of the phase space of the macrostates, right? If you change the way you partition the phase space, you change the entropy associated with a given microstate.
Very good point,
So
hold that thought. Okay. Extremely good point. I'll come almost directly to that.
I kind of missed the point of the Poincare recurrence problem that we were supposed to have with Gibbsian SM. So, you just say, I mean, if I have a stationary probability distribution, that's compatible with the individual system, passing through every state, including, recurring. It's the probability distribution that's that's stationary, not the state of the system.
Yeah. Well, this is why the set of problems I've raised here are not entirely separable out. The argument, I mean, I'm reconstructing someone else's argument. Basically, the dialectic goes something like this. Because any given system recurs, as long as thermodynamic properties adhere on given systems, we're never going to get genuine irreversibility in our derivation of thermodynamics. And so the way to get genuine irreversibility in our derivation of thermodynamics is to move from the level of individual systems to the level of probability distributions over systems.
Okay, and that's taking, okay.
And that's what's that's exactly what's driving Craig's title, yeah.
Yeah, okay, yeah, I remember talking about Craig about this.
So what I want to do is essentially go through that list and distinguish between criticisms of certain arguments for or defenses of the Gibbsian framework versus criticisms of the machinery of the framework itself. And I want to show that mostly you can see these kind of objections as being objections that are made to ways the Gibbsian framework is being defended or glossed rather than of the framework itself. So let me start with the issue of subjectivity. So here's the objection, and you'll see here where this is linking back to my earlier half of the discussion. Against probability distributions being used by the Gibbsian, a system's thermal state had better be a property of that system, and it better not be a property of our knowledge of the system. And against coarse graining, again, the approach of a system to equilibrium had better be caused by properties of the systems, not properties of how we measure the systems. So in both cases, so this is just spelling out the subjectivity concern. Okay, so here's the response. These are terrible from the dynamicist point of view, which is the minute I deem me to be speaking from. These are terrible accounts from that perspective of probability and coarse graining. But they're not necessarily the only accounts that are available for somebody who wants to defend the Gibbsian framework. And those concepts, suitably understood, are a necessary part, this comes back to the next point, necessary part of Boltzmannian statistical mechanics as well, as we've seen. So just reminding ourselves on the probability case, we've seen that if we want to give a sharp formulation of Boltzmannian statistical mechanics, it's got to be a formulation that includes the assumption that probabilities are given by the Liouville measure conditionalized on the state, or maybe given by something that's not too sharply there in respect to the Liouville measure, or something like that. But in any case, an assumption of that kind has to be in Boltzmannian statistical mechanics. It's an essential part of the machinery of the theory. And that probability, certainly as argued by the kind of strong proponents of the neo-Boltzmannian framework, at least they've got a point, it's difficult not to make those probabilities objective. Insofar as they can't make them, insofar as you can make sense of it without the probabilities being objective, then plausibly that way of making sense of it maps back to the Gibbs framework anyway, but the normal assumption here is they need to be objective. Okay, and sure, it's not clear how we can understand objective classical probabilities. This comes back to what I identified as the most serious problem for the dynamicist conception of classical stat mech, but that doesn't pull the Gibbsian and Boltzmannian concepts apart. So the idea that having a certain probability of being in a given state can be an objective property of a classical system is something that's already on the table from the Boltzmannian point of view. So although the way the probabilities in the Gibbsian framework are normally glossed is inimical to the dynamicist defender of Boltzmann's perspective, the very presence of those probabilities should be just fine. If you look at the coarse graining side of things, as I said, the coarse grain Gibbs entropy is a function of the fine grain distribution. So, I mean, here's the kind of straw man concern. So one sometimes has the worry that what the Gibbsian approach to statistical mechanics to equilibrium is supposed to be doing is saying coarse grain evolve, and the reason we're justified in doing that is because we only have coarse grain knowledge of the system. But that's not how, we don't have to understand the way coarse graining works in Gibbs for that to be the case. And here, to some extent, I'm reprising my Zwanzig framework from earlier in a more special and more limited case. The fine-grained probability always evolves under the Liouville equation, which I've just written in a completely schematic form there. And the coarse-grained dynamics, just mathematically definitionally, are the dynamics we get by evolve coarse grain, evolve coarse grain, evolve coarse grain. But if we have the same commutativity we saw on Monday, if I get to the same place using the coarse-grained dynamics, as I do if I use the original dynamics and then coarse-grain at the end, then I'm licensed to use the coarse-grained dynamics to predict the evolution of the coarse-grained part of rho under the fine-grained dynamics. So we can perfectly well understand the dynamics as genuinely being unaffected by our ability to measure the system, and yet our machinery to predict the evolution of the coarse-grained part of the distribution as given by the above, insofar as that's a reasonable dynamical assumption. Is it a reasonable dynamical assumption? Well, it's certainly not something that can be in any way proved under this program, but the Boltzmannian is already committed to the use of kind of reasonable sounding but falling far short of proof assumptions in the way the mathematics is set up. So we'll only, to achieve parity here, we'll just need to make that plausible. Okay. Then we talk about entropy as part of single systems. This is the second objection that I put on the table in my kind of quick Boltzmannian summary. So entropy explains system's actual thermodynamic behavior. Given that, it had better be a property of the actual system, i.e. better be a property of the microstate that actually describes the system. Fair enough. But remember, from a Boltzmannian point of view, the claim that systems equilibrate, the claim that their entropy go up, is a probabilistic claim about the system. And it doesn't seem unreasonable that the property of the system that leads to a certain probabilistic fact about its behavior is a probabilistic property of the system. So insofar as we're allowed to talk about probabilistic properties of systems, which I've argued needs to be licensed on the Boltzmannian conception of stat-neg anyway, it doesn't seem obvious what's so problematic about saying that the entropy itself is a property of the microstate. It's a probabilistic property. It's not a property you can read off from the classical dynamics alone, but it's nonetheless something that we're supposed to be understanding as a property of the system. Yeah.
I'm a little, let's see. So it seems to me right to say that a Boltzmannian needs to talk about a probability distribution over initial conditions or something like that.
Yeah.
But what you're talking here about a probabilistic property of an individual system, that seems like, that at least evokes in my mind some way of going from a microstate to a probability distribution. There wasn't any previously any need for anything like that in the Boltzmannian program, was there?
Well, it's going to depend how loose your notion of property here is. I mean, how does the Boltzmann explanation of why the system equilibrates goes? It says something like, well, the equilibrium region is really, really big compared to the current region.
Right.
So, so the current system with really high probability is going to make its way here.
No, but I don't understand. Everybody understood that kind of argument. I mean, like you're saying, at very, to describe it very, very generously, it's a first pass at trying to make things plausible. And of course, you want to do much, much better. You want to have a much more detailed dynamical account to the extent that you can. All I'm getting puzzled about here is, so the Boltzmannian wants entropy to be an attribute of an individual system, and what Boltzmannian does in order to make that the case is give a prescription for assigning an entropy to an individual microstate. By analogy, it sounds like what you've got in the back of your mind here is a way of assigning a probability distribution to an individual microstate. Is there some algorithm you have in mind for going from an individual microstate to a probability distribution, in analogy to the way we have of going from an individual microstate to an entropy?
Yeah, there's the terrific book I read that suggests it, which says start with the past hypothesis, evolve forward and condition the present state.
No, but I see. So the idea would be, no, I still don't get it. compare it, I don't want to hold it, maybe I'm just missing something and I want to hold it up here. But compare it to the way of assigning entropy to a microstate.
Yeah.
Okay? There's nothing about history, there's nothing about anything like that. I simply have a carving up of the phase space into macrostates, identify the microstate, I have a prescription for getting that.
Right. So there's a disanalogy here. So the entropy on the Boltzmannian conception is a property, is determined just by the phase space dynamics and by the partition. This comes back to Nick's point, which I'll come to in a second.
Right.
But the probability distribution is determined in addition by other assumptions in the theory. But it's still an objective fact about the system that its probability of being in the given state is given by this particular rule. At least if it's not an objective property, I'm going to have to make sense of the work.
But so I don't start, I mean, another disanalogy is I don't start there from a microstate. Okay.
Yeah.
I see. I assign a probability to, okay.
Yeah, the claim is not that there is an analogy between the Boltzmannian and Gibbsian way of understanding of assigning entropy.
Right.
It's that assigning the Gibbs entropy is can be done using resources to which the Boltzmannian is committed.
Okay.
I had some worries that was probably similar, perhaps probably not, but some of your discussions. Can I summarize this by saying that on the Boltzmannian picture, at least presuming that we have a fixed carving up of the phase space into macrostates, entropy is not a probabilistic property, but that things like increase of entropy or approach to equilibrium, which will depend on and this is a probabilistic affair in the sense that even Boltzmann can only say this occurs with
Exactly. Yeah. But that brings to the other point, and this is my kind of filling in the preliminary note to Nick. While Boltzmann entropy is a property of microstates, it's not a property of the microstate in any way which by itself is dynamically or causally efficacious. If I know what the Boltzmann entropy of a system is, and that's all I know about the system, that tells me basically nothing at all about what it's going to do in the future, virtually nothing. I certainly can't deduce from the fact the system has a low Boltzmann entropy that it's going to evolve to a higher Boltzmann entropy state. I can't deduce anything at all. Yes, it's back to David's, what part of I haven't a clue do you not understand. So, I mean, just here's a way to make that vivid. I mean, suppose I've got some system, and here's its current state, and this is the trajectory it's going to take. And suppose it's in this macrostate, according to which its entropy, remember, is the log of the size of this space. And suppose I were to change the, remember that the macrostates are partitions of the energy hypersurface. So now suppose I change the Hamiltonian of the system in such a way as this macrostate gets way, way bigger, but I don't change the Hamiltonian in the vicinity of the system. Now in doing so, I've substantially increased the entropy of this state, but not in a way that has any effect at all on its dynamical position. So it's important that the Boltzmann entropy is only causally efficacious in combination with non-categorical features of the system, or non-categorical modulo Humean reconstruction, but prima facie non-categorical properties of the system. And so I think once we've decided that the kind of Gibbsian theory we're discussing is one whose probability measure is thoroughly objective, it's not clear to me that the Gibbsian account is at a particular disadvantage here. In fact, you might think that the account kind of tries to package up in the same place the two components for the Boltzmannian, if you like, present-day macrostate plus distribution over it that are doing the work, the probabilistic and non-probabilistic parts. I don't know how far you can push that suggestion, but it's at least as a kind of first pass. Okay, give me time. Let's. Oh yeah, sorry. And the last point, just as a reminder that probabilities are necessary for the Boltzmannian. Well, for anybody who wants to recover the results of statistical mechanics, and therefore a fortiori for the Boltzmannian, having probability in the theory is necessary not just because it's some piece of foundational ingredients, but because lots of the predictions of statistical mechanics are probabilistic. I had in mind when I did this things like fluctuation phenomena, but actually John reminded me that we have plenty of non-equilibrium stochastic dynamics like Brownian motion, which need to be understood that way. Of course, that's not to say that these notions can't be glossed in terms of something like long-run relative frequencies or something similar, but that's an objection that kind of cuts across the Gibbs versus Boltzmann framework question. Okay, let me think about the third issue. Gibbs entropy invariably increases. So just, this is reprising in a bit more detail what I was saying to Wayne a second ago. So it is supposed that Gibbs entropy invariably goes up, whereas Boltzmann entropy can go up and can go down.
Coarse-grained Gibbs.
Say again?
Coarse-grained Gibbs.
Yes, coarse-grained Gibbs, thank you. And so Boltzmann entropy is supposed to deal better with the probabilistic nature of stat mech and with recurrence. Here's a response to that. Insofar as the dynamical framework we're describing the system in is supposed to be one where I'm allowed to be using the coarse graining, fair enough. But what that points to is that if we want to think about the Gibbsian framework properly, in these situations where fluctuations could be occurring, we need to start talking not just of how the distribution evolves, but of how the evolution of that distribution assigns probabilities to given sequences of macrostates. So I'm going to just quickly dump a small chunk of formalism on that. Let's talk about how, if we know the evolution of a probability distribution, we can work out what the probability is of a given sequence of macrostates. So partition the phase space into macrostates, Boltzmann style, such that knowing and choose a discrete sequence of times. So if we know the system's macrostate M1 at time T1, M2 at T2, M3 at T3, we've got the macro history of the system at a certain level of coarse graininess both in space and in time. And let's just say my use of branch here is an attempt to subliminally indoctrinate you into Everettian propaganda. We say a branch or a history of length n is just sequence of macrostates, one for each time, up to n. And the idea is each branch is a particular way the macroscopic affairs could turn out. And we want to know how the density operator in its evolution assigns probabilities to each branch.
So just check, is that T sub big N?
That should be T sub large n, yes, thank you. That's one of those deliberate mistakes I warned people about earlier. There's more to come, by the way.
But does that mean that the number of times is equal to the number of macrostates?
No, so Neil, I take it you just mean the second little n. Right, so this should indeed be an arbitrary little n, but this should be capital N.
But the M1 through Mn doesn't need to be the same big N, right?
Oh, I see what you mean. No, that's true. Those are different ends.
Is one perhaps a capital mu? A capital mu?
Exactly.
Yes.
Do you read, if anyone ever reads Carlo Rovelli's book on quantum gravity, it's a lovely book, but it's absolutely thick with these places where he says things like, do bear in mind that bold E subscript little I does not mean the same as italicized bold E subscript little I. They turn out not just to be not the same, but to be completely unrelated objects. Anyway, so people get the general framework. I want a sequence of macrostates, a sequence of subsets of the phase space, and each of those is a kind of macro level description of the history of the system. And that's just terminology. Extension of the history is just put some more terms on the history. So, let me show you that on paper rather than dumping it on you. So, say you want to work out what's the probability distribution, what's the probability distribution conditional on the system being in macrostate M1 at T1, M2 at T2, M3 at T3, etc. So if you think what you want to do there, you want to start with the original probability distribution. You want to restrict it to macrostate M1. You want to evolve the restricted distribution forward. You want to restrict it again to M2. Evolve it forward, restrict it, evolve it forward. And at the end of the day, you just want to normalize. You just think about the conditional probability formula. The way you conditionalize a probability distribution is you just truncate and renormalize. We might as well do all our renormalizing at the end to keep maths under control. So if I write pi rho is defined like this, So pi I rho of x is just the restriction of rho to the ith macrostate. And if if this thing is the evolution equation for the system, then I now want to start with rho. I project.
So those are MIs.
Those are MIs.
The I's are almost microscopic.
Yeah, so just for simplicity, if I suppose, I mean, you need a more general labeling convention. I just suppose that the first that I'm looking at the particular sequence M1, M2, M3, M4, just to make life simpler. So I project onto the first one. I evolve to the next moment in time. I project onto the next one. I evolve to the next moment in time. Eventually, I project onto the last one. So my final distribution, it isn't that because I need to normalize. And to normalize, I just need to divide this through by the integral of rho over the whole space. So,
And sum over all the i's in the case.
no, actually, not to normalize it. That will just give me one. The way I conditionalize is truncate and normalize. So to normalize this function, I just need to work out how big it is.
Okay.
So that's probability is conditional on the first n steps
Exactly.
being that particular
This
step.
is the probability distribution conditional on those n steps having those results. And then this thing at the bottom is just the probability of them having that result.
So you conditionalize on 1, 2 until n.
Exactly.
Good.
So conditionalize, evolve, conditionalize, evolve, conditionalize, evolve. What I should strictly do is every time I conditionalize, I should renormalize. I've just done all my normalization in one go.
I've just lost track now of why we have this sequence of macrostates. I mean, as time unfolds, you project on the different macrostates.
Yeah.
Just remind me again, why are we doing that?
Okay, so what I've got on the board for simplicity here is just what I get if the particular history I was interested in was M1, M2, M3, M4, M5, M6. In general, this one would have to be the index of the first one, the index of the second one, and so on.
Okay, so our system will truly, you're assuming our system happens to end up at those times in the macrostates that you're now conveniently labeling.
Exactly. This is the special case where my labeling is carefully
Your labeling has been preordained by God to work perfectly.
Exactly.
Okay,
So in the general case, the formula looks like that.
It will look even worse. It's going to
Except I need I've left the row out on the right hand side here that modulo that's the general case, you see. So now I'm projecting onto the first element of that history, evolving, dot, 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 project onto the n-1th element, evolve, project onto the nth element. So that's how the evolution of a probability distribution determines a set of probabilities over macrostates. But that's just math. It's not. There aren't any assumptions going into that. Okay, so now let's talk about the.
A hell of a lot of it. I mean, you'll get very different results depending on the time intervals at which you decide.
Oh, well, there's a huge amount of assumptions will go into any given answer, but that formula is just maths.
Ah.
Can I just check?
Yeah.
There's a difference between the board and the slides. So the slide is a sub J on the use.
Yeah, that's a typo, sorry. Ignore that. What I'm about to go on to say is that if the dynamics and macrostates and coarse grading are all appropriately chosen, in the usual, what was David's phrase, Jewish proof kind of way, on those assumptions, then the assumption would be that we could replace it. So I kind of anticipated that up here, but that's just a mistake. Okay, why do we care? Well, with that kind of framework available, we can actually work out how the Gibbs entropy change is conditional on it turning out to have particular macro states at given times. I have in the mind here, at the back of my mind, how one thinks about this in a kind of Everettian decoherent history framework, but at the moment this is just a formal similarity, it's sort of classical mechanics at the moment. So you can construct easily enough what the coarse-grained entropy is of rho relative to branch H. So that says that conditional on the events of branch H happening, what's the Gibbs entropy? And you can prove easily enough, given my formal compatibility requirement, that if this a while, never mind that kind of setup. Yes, that's right. So take take a history H. Take all, and it's kind of helpful here if you like to make life simpler, is just mention the trivial history where nothing happened so far. Think of all of the histories H prime of some particular length. So all the ways things could go over the next n steps. And you can show that the branch relative Gibbs entropy, branch relative coarse-grained Gibbs entropy relative to the history H is less than or equal to the expected value of the Gibbs entropy over all the various ways things could go, plus this expression here, the H prime here should be there, sorry, it should be subscript. That piece should be there. Why have I given you that slightly unlovely piece of mathematics? The point is something like this. Remember when we came into this, the Gibbs entropy, the Boltzmann entropy, or the thermodynamic entropy ought to be able to fluctuate down. The Gibbs entropy can't fluctuate down as long as the coarse-graining assumptions are valid. The branch relative Gibbs entropy can fluctuate down. It can fluctuate down either because, let me back off a minute. It will go up on average provided the term is negligible, because this is the expected value of it later in time. So on average it will go up if this term is negligible. But even if this term is negligible, say for instance because the dynamics is almost deterministic at the macro level, then it could still be the case that through low probability it fluctuates down. And in fact, it could be, and here we have kind of Maxwell-Demon points in play, it could be that the Gibbs entropy goes down even on average because the measurement is extremely indeterministic at the macroscopic level, and so this term is quite big. So the kind of take-home from that, if you got lost in the technical details there, is that if instead of the Gibbs entropy you keep track of the Gibbs entropy relative to a branch, then you find it has just the properties that the Boltzmann entropy has, and just the properties that thermodynamically we might want it to have, which is that it's capable of fluctuating down just through random low probability fluctuations, and in fact it can go systematically down in particular interventions where which lead to wildly macro indeterministic dynamics.
You just say again what the H and the H primes are?
Right, the H is some particular history, and the H primes are extensions of that history to later. So imagine.
So this is some particular history that is compatible with the dynamical equations.
Well, these are macro histories, so no, they don't have to be macro dynamical equations. But remember, because these are macro histories, probably almost any history is compatible with dynamical equations in the sense that there are some trajectories that thread it. So you can think that. Again, suspiciously Everettian labeling, some liminal issue going on. Yeah.
I've got a point that's worrying me now. You have, of course, defined extensions by taking a given history and regard that as an initial segment of what is going to extend it,
yeah,
right?
That's right.
we could also extend the history by choosing additional time points in between and perform measurements on it, or we could have a prefix added to it. I assume, at least that's my intuition, that formula you obtained is going to apply to those kinds of extensions just as well as to the extensions later, the kinds that you...
I have absolutely no idea.
It might be that your condition of forward compatibility will be might differentiate.
Yeah, cut it up too fine and you'll break forward compatibility.
But otherwise, the properties of entropy and so on, I just talk usually about giving a more detailed description, and it doesn't matter whether that more details will be in the future.
That's probably right. The only reason I'm slightly cautious is, remember, this Sj is an increasing, because of the J superscript, there's an increasing quantity with the course grade. Because of the J superscript, yes, the total entropy is an increasing quantity. So I'm not sure how that will play if I go back in. So if I think about, if I work out the total, if I look at the entropy of the full distribution at some later time, I know it's higher than it is at some earlier time. And so that gives me, that lets me have an inequality there. I don't know how that will play out if you put it in intermediate times. But I mean, just more generally, just in terms of the framework here, I'm taking, the kind of way I'm thinking about macroscopic histories here is kind of really taking the time division just as with the macrostate division, as just a kind of entry parameter to the problem. So choosing a finer time partition would be like choosing a finer microstate partition. And that's just iterative, that's how I'm understanding the framework.
What happens if I just run this in the reverse time order? I take a sequence, I take the history just to be sequences of macrostates going backwards in time, and then will I get the same results coming out?
It'll break explicitly because there's an explicit violation of time reverse invariance going in the construction of the coarse-grained dynamics.
Where was that?
Well, only in the sense that I stipulated that I had forward compatibility with the coarse-grained dynamics and said nothing about the backward compatibility.
But you could do it. You could, of course, evolve backwards, coarse-grained, evolve
you
backwards.
can't. I mean, this gets into the mechanics of the coarse-graining. It's slightly off topic, but for what it's worth, I mean, you can't in general impose. You won't generally have both forward and backward compatibility with the same coarse-graining. I mean, just quickly why. I mean, if you've got a coarse-graining, then entropy generically goes up. So if coarse-graining works in both directions, entropy generically goes, coarse-grained entropy generically goes up in both directions. Obviously, you can only do that if it's constant.
Yeah, so the idea is you've got to pick the sequence of macrostates such that the underlying such that there is some adaptation of the underlying dynamics. Otherwise, you don't have.
Exactly, and the kind of the justification for this in this framework is only. It's got the same kind of heuristic, like kind of plausible status as equivalent assumptions in the Boltzmann framework. And in fact, I'll make that connection much closer in a second.
Yeah, but well, I don't want to keep you up, but clearly the condition of forward compatibility is not as innocent as one might.
I don't think I claim it's innocent at all.
It's
a strengthening, and I think it's a full mathematical matter, considerable strengthening, but in terms of circumstances in which one we led to think it was heuristically likely it was true, not a very strong strengthening of the earlier assumption I was needing to make that it just works as coarse-graining projection in originally setting up the Gibbs dynamics. So my original starting point there was that was the kind of heuristic hand-waving dynamical assumption that's being made in the Boltzmannian framework anyway. So from the point of view of the dialectic, it's in the range of acceptable moves. As in, one of the things I take it is not a legitimate criticism of the Gibbsian framework from a Boltzmannian starting point. It's a complaint that his mathematics is insufficiently rigorous.
Yeah. I'm not saying it's illegitimate when I'm saying it's not innocent.
Oh no, I hope I was completely clear. It's guilty as hell. I mean, I also think we have extremely strong heuristic reasons that extend beyond merely heuristic in various concrete models and can be done. You know, we have cases where we can do it in perturbation theory, but yeah, no, sure, it's not intended to be trivial. And you can, in a sense, you can see it's not trivial because it brings in a time asymmetry. I mean, so somewhere in the story, time asymmetry, I mean, and of course the place it came in is again just borrowed from the Boltzmannian, and it's imposing a particular smooth probability distribution at a particular time. So it's a violation of time translation symmetry rather than time reversible symmetry. Okay. So yeah, that's just some of what I'm saying. So the point being, if you work through the details of what the Gibbs entropy does when you keep track of the actual macro history, you find it shows the same kind of features that the Boltzmann entropy is supposed to show, i.e. random fluctuations in general with really low probability, plus the possibility of systematic decrease given the right macrodynamics. Okay, so what I want to go on and do from that is to kind of show all that in a bit more detail within the Boltzmannian framework itself. So what I want to do is make explicit what I take to be the technical assumptions doing the work in the Boltzmannian framework in a fairly rough and loose way, and show that the statistical mechanics you construct applying the Gibbsian machinery in the framework I'm talking about, you know, in the way I've set it up, gives you something back that is essentially Boltzmannian statistical mechanics, or has a very straightforward mathematical link to Boltzmannian statistical mechanics. So here's my quick sketch of the technical assumptions that are being made for the Boltzmannian process to work. So the first point is that if I have a uniform probability distribution over a macrostate, for reasonable future times I can expect that distribution to be overwhelmingly concentrated in some macrostate or macrostates of larger volume. That's the requirement for entropy to go up. Remember, the entropy in this framework is a logarithmic, is the logarithm of the phase space volume. So the statement that the entropy is extremely likely to go up is the statement that the overwhelming majority by phase space volume of points in a region of a given volume are going to end up at a given time in a region of larger volume. And then the second assumption is that the first assumption is not spoiled if I conditionalize the uniform distribution on a sequence of earlier macrostates.
David, I guess this is related to my last question. Just to clarify, when you say that's an assumption of a Boltzmannian approach,
yeah.
I'm not sure I understand. That's something that one wants to get to come out true on a Boltzmannian approach, but the aspiration is to derive it.
Right, so when I say technical assumptions, what I mean, one person's postulate is another person's derivation, and the other person is better at math. So what I'm saying is that the things that will happen, whether 1 and 2 is true of a given system is in principle, modulo the fact that they're not very precisely stated, a mathematical fact about the system's dynamics alone.
Right.
Dynamics plus partition alone.
Right.
The Boltzmannian needs it to be the case that those results are true,
right.
and might aspire to derive that they're true, but in any case, to run their machinery must be true.
Yes.
So that's what I mean by this.
Yes.
If you want to replace assumptions by requirements, that's fine. So the kind of mechanical systems to which Boltzmannian statistical mechanics are applicable are mechanical systems with these characteristics.
Sure.
So the second one I need, because it needs to be the case that if I have, say, macrostates, is C, is B, is A. It's not enough for it to be the case that the uniform distribution over B nearly all ends up in C. It had better be the case that the quite small subsection of the uniform distribution of B that you get by mapping forward the distribution of A also mostly ends up in C. That is, if B contains its kind of really small, awkward, anomalous regions that don't end up in C, it's not enough for those regions to be really, really small. We also require that A mostly doesn't get mapped to them. So A, normally we assume, because A is kind of, these regions are unimaginably scattered across B, and the dynamics doesn't kind of home in like a laser on those regions, it kind of smushes it out a bit. But anyway, those are the assumptions we need to be in play for the Boltzmannian storage of lambda.
In case of Boltzmann, there might be maybe an Austrian proof, which is simply to say that this is what I have proved.
Truly marvellous proof of this fact. Right. So here's how I'll show. Here's now how I'll construct a Gibbsian statistical mechanics for that system. So the first thing is I use the macro states themselves to define a Gibbsian coarse graining. So remember, the way a Gibbsian coarse graining works, at least in a nice simple version, is I smooth the probability distribution uniformly over each macro state. So nothing prevents me using the macro states themselves as the definition of the coarse graining. One often finds in the textbook treatments the suggestion that the Gibbs coarse graining would ideally have cells all of equal volume. These are cells of radically monumentally unequal volume, but there's nothing in the framework I've set up that requires equal volumes. Okay? Under that coarse grading, if you work out the Gibbs entropy, minus rho log rho, conditionalized on a given sequence of macro states, what you'll find is it's just the log of the volume of the final macro state. You can kind of see what it is, yeah? If I take a distribution, to run it forward, I take a distribution, I conditionalize, I evolve under dynamics that includes coarse graining, and so smooths it all out again, I conditionalize again, I keep doing that. At the end of that whole story, I get a smoothed out distribution restricted to the last state. So the coarse-grained Gibbs entropy for a history of a given macro state is the same as the Boltzmann entropy for any point within that macro state. And the technical assumptions made amount to the assumption that the coarse graining I've just defined there forward commutes with the dynamics. This is Yoss's non-innocent, my non-innocent assumption. I can't palm it off on yours. But the requirement that that particular coarse graining is forward compatible, which is the requirement that I can use it to I can use the coarse graining to calculate the probabilities rather than having to use the underlying microdynamics, that's just the same as the assumption I just made of the Boltzmannian dynamics. The assumption I made of the Boltzmannian dynamics is that if I want to work out where this system goes, then it will end up overwhelming probability in one particular in these particular places, and it won't be affected at all by its earlier historical development. So it's the same requirements as have been made for the Boltzmann. And so if I make the assumptions that ground Boltzmannian statistical mechanics, I also ground Gibbsian statistical mechanics, and I get the same entropy at every time. Sorry, yes. If what I mean by entropy here is the branch relative entropy. Okay, so there's a mathematical equivalence going on. Is it a conceptual equivalence? Well, maybe, maybe not. But there are some differences. Here's an important difference to flag. The concept of equilibrium we have in play will be different in this kind of story. The Gibbsian concept of equilibrium says that the system reaches the system's equilibrium if the coarse-grained distribution is uniform across the energy hyper. I said phase space, but I mean the energy hypersurface. For the Boltzmann, it needs to be in the largest volume macro state. So there's a difference there. However, remember that we need to get fluctuations out, even in the Boltzmannian framework. So it's not actually enough for the Boltzmannian approach to be empirically adequate that the system is overwhelmingly unlikely to be in the largest state. Its probability of being in any given state has got to be proportional to the volume of that state on the energy hypersurface, otherwise the fluctuation phenomenon won't come out right. If the system is with if after equilibration the system with 100% probability is in the largest macro state, then the system with 100% probability will not fluctuate. We can measure fluctuations. I mean, not for systems this big, but in general. So the Boltzmannian, even if the Boltzmannian characterizes equilibrium by being in the largest volume macro state, it better also be the case that after the equilibration timescale, the system has a probability of being in states fluctuated away proportional to the volume of that area. For systems like an ideal gas with a mole of particles in, you're not going to see this, but for mesoscopic systems, you can see it and reduce it. So both approaches actually agree on what or had better agree. This is a friendly amendment to the way the Boltzmannian program is sometimes presented. Had better agree on the probability distribution over macro states after the equilibration timescale. Now at that point, it seems to me the difference is becoming largely a matter of semantics. The Boltzmannian says that the system fluctuates away from equilibrium, it fluctuates into and out of equilibrium. The Gibbsian says that fluctuation phenomena occur at equilibrium, but it's not particularly clear to me that there's a substantive matter at stake here.
But part of that difference is also going to be lost in the terms that for Boltzmann, there will also be a fluctuation in the entropy value.
Yes.
As the system moves away from equilibrium.
Yeah, and they won't be here.
And in the Gibbsian framework, entropy stays the same, although there are fluctuations, but there are fluctuations in energy or whatever you have, not fluctuations in probability.
Agreed.
And that distinction is important in when you have Einstein's use of the Boltzmann principle to talk about fluctuations in entropy.
Yeah, I take that point. I hadn't really thought about it, to be honest. My immediate response is to think, well, granted that if both of them agree with the probabilities of all measurements that are made, then it can't be that this can be a substantive difference. There must at some level, again, be a matter of a definitional character, but I take the point. And I should say, here's one place where I think there is some advantage in the Gibbsian way of thinking as well. I mean, if I have situations where the macrostate is not, where the biggest macrostate is not overwhelming the biggest, then there are virtues in thinking that way. A concrete example would be that nothing, and this is just a textbook example, nothing prevents us thinking about a single molecule in a gas as having equilibrated in contact with a heat bath consisting of all of the rest of the gas. I mean, you perfectly well run normal StatMech routes to determine its equilibrium state, and it's one way of getting out the Maxwell distribution. That's a slightly less trivial example would be John's example of Brownian motion, where I can perfectly happily say that the pollen grain has equilibrated, and I'm going to understand that in the Gibbsian sense of it, but there isn't really a good Boltzmannian conception of equilibration, because there isn't any particular macrostate of the pollen grain that's dramatically more likely than the rest. However, this is only really relevant in these mesoscopic cases. For the kind of macro systems, and it doesn't seem to be a great deal at stake there. Okay, so let me sum up. Confused is too strong, perhaps. The neo-Boltzmannian critique of Gibbsian statistical mechanics can be understood as a criticism of rather bad explications and understandings of Gibbsian statistical mechanics, granted ones that are extremely widespread in discussion, and don't need to be understood as problems with the approach itself understood formalistically and mechanically. Understood that way, the conceptual technical machinery it requires is stuff that the Boltzmannian approach requires as well. And I claim this slightly more tentatively, but it seems to me that it's not clear what the fundamental difference is once we've omitted an objective notion of probability into our theory in the first place, between making probabilistic claims about how a system's actual microstate evolves and just making deterministic claims about how the probability distribution over the microstate evolves. These are just different ways of handling the same underlying physics. We see this in cases in non-equilibrium StatMech. There's no fundamental difference between using the direct equations that govern Brownian motion to describe stochastically what the individual particle does versus using the Fokker-Planck equation to describe how the probability distribution of the particle over velocity space evolves. And in the regime in which Boltzmannian statistical mechanics is valid, and was on the mathematical assumptions required to ground Boltzmannian statistical mechanics, the approaches coincide or at least come extremely close to one another. And just to an epilogue, and this brings me back, if you like, to the stuff I was saying at the end of the first half of the lecture. Again, perhaps I'm slightly overreaching here, that in quantum statistical mechanics, there is much less need for additional probabilistic assumptions over and above the quantum probabilities. And in particular, the distinction between microstates and probability distributions, at least at the level of any given application, largely goes away. The right way to understand the quantum state assigned to a given system, albeit perhaps not the universe, is going to be as a particular mixed state of the system, not as a distribution over such states. And in that regime, quantum states in general, in the classical regime, insofar as we understand classical mechanics as an approximation to quantum mechanics, we're going to find quantum states in general, whether they're pure or mixed, end up corresponding to probability distributions rather than phase space points. And if this was more a quantum mechanics discussion, I'd talk a bit about the Wigner function and about the mathematical aspects of that relation. But for the minute, just to say qualitatively, you think about the way mathematically you tend to describe macro level quantum systems in regimes in which classical dynamics works, it tends to be via the Liouville equation, not via the Hamilton equation, at least as the first step. One sometimes will go from one to the other. And so, when we take quantum mechanics seriously, it's not clear that the basic conceptual differences between the Gibbsian approach conceived of dynamically rather than inferentially and the Boltzmann approach can even be cleanly formulated. Okay, amazingly, I've finished in time.
Have you written this up somewhere? Is there a document we
yeah, the first half of it is on the archive, and I think on PhilSci archive as well. The second half is written up, but I haven't. I haven't done the references stage yet, so I can certainly say I can send you what I have anyway, but it'll probably be. I'll try and put it up next week. I can't do references on the road very easily.
Is there a time of the first one?
Inferential versus dynamical conceptions of physics.
Don't know what exactly you would count as under the basic conceptual distinction between two approaches, but certainly even in quantum statistical mechanics, we can either talk about states as being represented by density operators, and a more straightforward Boltzmannian idea about talking about microstates now being represented by projectors as the natural correspondent of regions in phase space in the original case, right? That aspect of a conceptual difference can be translated.
Yeah, agreed. I agree that's right, but on the construal of Gibbsian statistical mechanics I'm making here, it eventually is itself making use of the projection machinery to define branch relative ideas. Yeah. So that too comes across. So it depends. Well, I mean, to some extent, it's a semantic question of which you call the Gibbsian part. If you want to say that the introduction of macrostates and of the notion of branch relative dynamics is it doesn't count as Gibbsian, then you're right, of course. But then that would also be a legitimate concern of what I said on the classical side of things. So you can think about, if you want to think of that as a friendly amendment to the Gibbsian framework, that's fine, although I don't think it's really original to me. No. The other point, just as an interesting technical lesson point, is that if you try doing that Jos, I'm sure you know this, but just as a point to students, if you try doing this framework quantum mechanically, what you find in general is that the framework I described of project and evolve doesn't reliably define a probability measure at all. Understanding the criterion under which it does define what is one way to get at the theory of decoherence.
Can I ask one more informational question? Is this procedure you just described in particular, because it's proof, so the condition of having forward compatible dynamics and having the increase of entropy, is that a particular application of the Swansea approach you described earlier? Independent?
It's not independent, but it's not quite a particular application. The Swansea approach, as I set it up, will give it'll give forward compatibility in the first sense that I described, i.e. before bringing in histories and decompositions. It's not quite strong enough to deliver the history framework in the way I've got it. It seems highly likely that in practice it would. You'd have to have very weird tangling between options to prevent it working, but it doesn't formally tail it. You can clearly see some relations here. I mean, part of this brings out there are very, the mathematics here I more or less borrow from decoherence theory, but there are very clear relations that aren't even really analogies. They're different people studying the same field from different sides, between the technology of non-equilibrium stat mech and the technology used in decoherence theory.
Just one thing about the first point in the epilogue.
Yeah.
there is, you know, well, so this goes back to what we started to talk about before. You talk about, so you have some macro state.
Yeah.
There'll in general be, on either construal of what it is to be a quantum state, a pure state, or an arbitrary mixed state, there'll be a huge number of such states compatible with the macro information. And we know from time reversal arguments that some of them will be perverse.
Yeah.
So we're still going to have to, we need some excuse for neglecting those.
Yeah. Well,
It may, now one may have hope that there might be, you know, that quantum mechanics might be much more accommodating to some simple, non-probabilistic way of characterizing the ones we want to ignore, or guaranteeing that we're not on one of them, than classical mechanics was.
Yeah.
That remains to be seen.
That remains to be seen,
But we certainly need some additional assumption.
Yeah,
Right.
just on logical grounds.
Right,
Yeah.
right.
Yeah, I mean, that's why I hedged when I read out the quote and
Right.
didn't read it out literally.
Right.
The quote only reached it slightly. I mean, here's a way of putting it. There are two roles being played by the probability distribution in classical mechanics, in classical statistical mechanics, both of which for classical statistical mechanics appear indispensable. The probabilities are both necessary as our method of ruling out crazy states, and they're necessary to recover, to be an input source for the existence of probabilities in stochastic dynamics at the macro level.
Right.
If I simply said, if I had a categorical specification of the crazy states in classical statistical mechanics, and I just said the real state isn't crazy, that would not suffice to deliver classical statistical mechanics, because there's lots of stochasticity in classical macro dynamics.
Right.
In quantum mechanics, those come apart. Features of the individual quantum states, even of the pure states, are entirely capable of providing the macro probabilities, and in fact generically will. But there's still a need in quantum mechanics to have some constraint which rules out the cuckoo states.
Right.
It is enormously attractive to desire doing that in a non-probabilistic way, because it's enormously unattractive unless one's already got, well, particularly from a unitary quantum mechanics point of view without the buses, it's enormously attractive not to feel that we need to bring in additional probabilities whose only role is...
It depends on whether you've got one. You know, it depends. But also just, and this is probably a remark of nothing over above historical significance. Generically, in statistical mechanics, especially as an attempt to undergird thermodynamics, most of the transitions we're thinking about in the generic case are pretty much macro-deterministic.
But, yeah, plenty aren't.
Sure, absolutely. Right.
Just a tiny technical, I was still trying to get my head up on that evolution, around the evolution you talked about. When the evolution operator hits each time in that sequence, what's being evolved? Is it just the position of the system, or is it the set of states that are in the whole macro state?
It's the whole probability distribution row. Well, it's the conditional probability distribution row.
Right.
U of t here is an evolution map for distributions. It's in the first instance it's the in the classical case, it's that guy in the first instance. In fact, normally when I'm handling it, this is the projected dynamics derived from this. So it's the dynamics I get by mixing some coarse graining into that.
What I was wondering about then is, we always get the same result. I mean, you choose those points 1, 2, 3, 4, 5 at which you're going to do the what do we call it, the coarse graining or the collapsing. Are you going to get the same result at the end if you use different intermediate states? Do you have insensitivity down? I can see you would if you're just evolving the point, but if you're evolving the whole state,
so I mean, well, you're not going to get general answers to this kind of. Most of the concrete models I know here are quantum mechanical, but rather classical. But what you would want in the kind of regime you're interested in would be the kind of instability to your time separations that we're supposed to have with respect to our macrostate choice. So it's a kind of requirement of the way we normally think about these macrostate setups that what we get out is not kind of hypersensitive to fine-grained or coarse-grained separation. So what you would expect to find would be that if you were to fine-grain the time separations or fine-grain the partitions, then at least up to a point, you would just be getting a fine-graining of the original stochastic macrodynamics. There'll come a point where that breaks. In the classical case, you'll always get well-defined probabilities, but they'll stop being the kind of thing that can be described by good macrodynamics. In the quantum case, you'll even have a break of the appearance, and it won't work as probability at all. But I mean, having said all of which, for the point of view of the description I was giving, most of the work is just being done by quite minimal facts about how entropy distributions evolve. So I'm not sure it would be crucial for this description. But in terms of generally how you want to do a Gibbsian macrodynamics, you better have that kind of insensitivity. I mean, you see this in the going back to my earlier Zwanzig framework. One of the criteria that says that you're in a range, this is heuristically useful criteria for when you've got a projection operator that's working where you want it to, is that the dynamics you get out should not be sensitively dependent on how often you choose to apply the operation. If you apply it too often, you'll get quantum xenotype freezing of the evolution. If you don't apply it often enough, you'll start getting weird extra stuff creeping in, but there'll be a big sweet zone in the middle where it doesn't matter very much.
So it seems natural.
So it had better be if it's doing what we want it to do.
Yeah, okay. And so I think I'm hearing what David calls the Jewish proof.
Yeah, I mean, it's like, this is slightly off route here. I mean, for situations where it's macro-deterministic, I can give you slightly better than Jewish proof. I can give you a physicist proof, which is I can do it for you. I can do it to second-order perturbation theory.
Those are most incomes
I mean, one of the interesting things about the Zwanzig, this is jumping back to last time, one of the things I think is interesting about the Zwanzig framework is while it has foundational significance, it's also quite significantly applied where the job is not to give a foundational underpinning for something, but actually to work out an equation. And so what you find there, as normal in physics, these kind of things, is people work in perturbation theory. And while proving exact results in that framework is no doubt tremendously hard, it's extremely amenable to perturbative expansion, and you can get things out of it relatively readily that way. I mean, possibly unusually in philosophy of physics, this is the problem of physics education. I'm really relaxed about perturbation theory. If I can prove if I can get things out to second order perturbation theory, I'm happy with it.
Any other questions or comments? It's redundant, I think it is.